Okay, hopefully the meeting will be recorded. So today we will discuss about simultaneous linear equations. So if you can recall, here was our topics that we are supposed to cover. The first one was the interpolation, and second one was the regression. We did the regression part in the offline lab. We were lucky, but we are unlucky that we may have to. By the way, okay, I will discuss about it. So today we will discuss about solution of simultaneous linear equation. The previous two topic was related to curve fitting. We were given some data, if you can recall. Interpolation was this thing. We were given some specific data points from any experiment, and our task was to fit a curve through the points. Okay, that was our task. And in case of interpolation, we fitted the curve exactly through the points, right? We fitted the curve in such a way that our curve passes through the points exactly. But in case of regression, we did something different. Like here was the comparison. So in case of regression, we tried to fit the curve in such a way that our error gets minimized. We assume that our experimental data has some kind of error, so we did not fit the curve exactly through the points. So our task was to minimize the error. We performed this experiment uh, in the offline session. I guess you wrote the code yourself as well. For the linear regression part, you have written the code yourself. Today we will discuss about simultaneous linear equation. That's the third experiment, and we can do two things. One of the two, you are supposed to give two simulation exams. Okay, you have to attend two simulation exams. First on the first three topics, and the second exam would be on the last three topics. Okay, the last three topics are numerical differentiation, integration, and roots of equation. The first experiment or the first exam would be on these three topics, and the second exam would be on these three topics. Both of the exams would be simulation exam. You may have to write some explanations, and most of the thing is that you have to simulate. You have to use MATLAB to solve relevant problems. Okay, so one option could be this.
আনুমানিক প্রথম এক্সামটা আনুমানিক কবে হতে পারে?
হ্যাঁ, এটা সম্পর্কেই বলতে যাচ্ছি। So we can have two ways. The first thing, that after completing this third experiment, in the next Friday we will arrange a problem solving session, and in a Saturday you can attend the exam. Okay, so the next Friday is 1st of April and Saturday is 2nd of April. So what you can do, the first option could be this. We are supposed to complete the third experiment today, and then on the 1st of April we will arrange a problem solving session on these three topics, and you can attend the first simulation exam on the 2nd of April. It could be one option. I guess it would be better. Or the second option is that we complete all the 6 experiments. We are not going to cover the 7th one, ordinary differential equation. Hopefully, if we get time, then we can try to complete the 7th one. But hopefully, we are going to cover the first 6 experiments. So the second option is we complete all the 6 experiments and then take the 2 exams back to back.
আমি স্যার মনে করি যে এটা হেক্টিক হবে, কারণ স্যার মানে ছোট ছোট করে আগালেই ভালো।
Exactly. So hopefully the best option would be that we complete the third experiment today, and then we will arrange a problem solving session in the next Friday, and then you can attend the simulation exam on the 2nd April, Saturday. Yes
স্যার, আমরা কি স্যার ল্যাবে আপনার মাঝে মাঝে প্র্যাকটিস করতে যেতে পারবো এমন কিছু?
এইটা না আমি ঠিক শিওর না, আমি যতদূর শুনেছি ল্যাব বলতে তো মূলত হচ্ছে আমরা যেখানে যে ল্যাব করি ইউবি 71309, তাই না? ওই ল্যাবটা হচ্ছে ট্রিপলি ডিপার্টমেন্টের ল্যাব, ঠিক আছে? আর অন্য যে কম্পিউটার ল্যাব গুলো আছে ওগুলো মূলত সিএসসি ডিপার্টমেন্ট, তো ওগুলোতে অ্যাক্সেস করা কঠিন। তো আমি যতদূর শুনেছি ওই 71309-এও খুব একটা অ্যাক্সেস দেয় না ক্লাস না থাকলে, শুনেছি, আমি শিওর না, একটু আপনারা দেখতে পারেন গিয়ে, ঠিক আছে? একটু গিয়ে দেখতে পারেন, এলটিও যিনি থাকেন মানে ল্যাবে যিনি থাকেন ওনার সাথে একটু ডিসকাস করে যদি উনি অ্যালাউ করেন তাহলে করতে পারেন, অসুবিধা নেই, ঠিক আছে?
তবে স্যার আমাদের 282 তে বেসিক্যালি তো আমাদের ল্যাপটপ দিয়ে কাজ চলছে, ম্যাটল্যাব, আর এমনি অন্যান্য ইকুইপমেন্ট গুলো লাগবে যেরকম মেইন কোর্স গুলোতে ওইগুলোতে বেশি লাগে।
হ্যাঁ হ্যাঁ, টু একটু মূলত আর কি সফটওয়্যার বেসড ল্যাবই আর কি,
এটা
হার্ডওয়্যার কম্পোনেন্ট তেমন একটা লাগে। দেখেন যদি আপনি চান ল্যাবে অ্যাক্সেস করা যাওয়ার কথা, একটু এলটিও যিনি আছে ওনার সাথে কথা বলে তাহলে, বা যদি এমন হয় তাহলে আমাকে নেক্সট ক্লাসে আমরা যখন যাবো আমি এলটিওর সাথে ডিসকাস করে দিতে পারি, যদি উনি অ্যালাউ করেন তাহলে আমি বলে দিলাম যে কাদের কাদের অ্যাক্সেস দরকার, তাহলে আমি হয়তো ওনাকে বলে দিলাম যে আপনাদের যাতে অ্যাক্সেস দেয়, ঠিক আছে? Okay, okay. So that's the tentative plan that we are going to cover the third experiment today, and then we will have a problem solving session on the 1st April in the next week, and then in the 2nd April you will have to attend the first simulation exam in person. Okay, in person means in the labs. Hopefully no one will have any issue. We will have problem solving sessions, so that we can have, or you can have a demo what type of problem could come. And by the way, you should submit the lab reports in the next lab as well on the 2nd April. As I guess you didn't have the opportunity to submit any of the lab reports, so please submit the lab reports by printing them in the 2nd April, on 2nd April. Okay. I will release some assignment as well that would be individual. Okay, we will discuss about it later. So move on to our today's experiment. Today's experiment is simultaneous linear equation. Okay, solution of. So can anyone guess what is this thing? What does this topic related to? Hearing the name of the experiment. হ্যাঁ বলেন।
Using matrices, using cost elimination.
Okay, so we will have a set of equation actually. Okay. So if we want to discuss about each of the words, simultaneous means we will have some equations and we will have to solve the equations simultaneously, means at the same time. Linear means we will have the order of the unknowns maximum 1. Okay, so we will have a set of equation like this. Let's assume we have a set of equation that looks like this. 5x1 or 5x plus thrice y minus twice z equals to 9. This is one equation. We have three unknowns here, right? We have x, y, and z, three unknowns. So we need three equations at least, right? We need three linearly independent equations. So let's assume the second equation is minus twice x minus 5y plus 9z equals to minus 5. And the third equation is what? It would be x minus twice y plus 5z equals to minus 6. So we have three equations and we are assuming that these three equations are linearly independent. Okay. So from these three equations, we know some methods already. We can solve the value of x, y, and z. Okay. So we already know about method of substitution, right? Substitution method or method of elimination, প্রতিস্থাপন পদ্ধতি, তারপরে অপনয়ন পদ্ধতি, তাই না? এগুলো আমরা দেখেছি। We know about substitution method or we know about elimination method. We know also about what? We know about Cramer's rule, right? I guess in Triple 203 we learned about Cramer's rule as well. So we know about Cramer's rule. So we are familiar with these things, but the issue is whenever the system becomes larger, so we have three unknowns here, right? So when the system is of 3 or 4 unknowns we have, then it becomes easier and we can also use our calculators to solve the system. But the thing becomes complicated when we have a larger system. Okay, let's assume we have a system where we may need to find the value of 6 unknowns. Okay, let's assume we have performed some sort of experiment, and from that experiment you have got some sort of relationship with the parameters. Let's assume uh, you are doing some sort of experiment, so one parameter there is pressure, one is the temperature. Let's assume one other is uh, we are considering the length of some material, so this is one other parameter. We may have what type of thing?
Density.
Okay, so we may consider the density of the material. We may consider the humidity or some sort of other parameters we may consider, right? So, and what you are trying to do, okay, so here is, so you have performed some experiment, and after performing some experiment you have got the relation in between them. Okay, so the first equation, let's assume, looks like this: 2.6 p plus 0.2 t minus 5.2 l minus 2.1 d plus 0.6 h equals minus 39. So we have this equation, and we will have 4 more equations as we need, actually 4 more equations to find the value or find the relationship of these parameters, right? So the motivation is, why do we need different techniques? We may be content with these techniques, right? If we have a smaller system, the number of unknowns are lower, then we can approach to this system like the substitution method or elimination method. Cramer's rule is actually a difficult method if the unknown becomes 4, because we have to take or find the value of the determinants, right? In case of Cramer's rule, if you can recall, we have to find the value of the determinants, নির্ণায়ক, তাই না? নির্ণায়ক বের করা কিন্তু কঠিনই ছিল, যদি 3 এর চাইতে বড় হয়ে যায়। So Cramer's rule becomes difficult when the number of unknown becomes 4, right? So these methods are okay whenever our system is small. We have unknowns like 3 or 4. But when the unknowns are larger in number, we have 4 unknowns or 5 unknowns, then these methods are not that much good to apply. Okay, they are not that much convenient. So in that cases, we move on to the numerical techniques for solving a system of linear equation. Okay, by the way, we are calling this system linear equation system because the power of the unknowns will remain 1. Okay, we won't get something like x square or x cube or y square y cube. Okay, as we are considering linear equations, so the power of the unknowns will be maximum 1. Okay, not more than 1. ঠিক আছে, যেহেতু আমরা লিনিয়ার বলতেছি, লিনিয়ার মানেই হচ্ছে এক্স ওয়াই জেড যে আননোন গুলো থাকবে আমাদের, আননোন গুলোর পাওয়ার 1-এর চাইতে বড় হবে না, কারণ 1-এর চেয়ে বড় হলেই তো ওটার স্ট্রেট লাইন থাকে না, তাই না? 1-এর চেয়ে বড় হলেই কিন্তু ওটা আসলে নন লিনিয়ার হয়ে যায়। So that's why we are calling it a set of linear equation, and we are using the word simultaneous because we have to solve the three equations at the same time. Simultaneous means we are solving it at the same time. That's why we are calling this solution of simultaneous linear equation. Okay, we are going to solve the value of xyz at the same time. That's why the name of the experiment is this. Okay, so I guess we have got an idea what we're actually going to do, or uh, what do we want. Okay, so whenever the system, so the bottom line is whenever the system becomes larger, means uh, more unknowns, then we move on to the numerical techniques. Numerical techniques becomes the savior then. Okay, it will help us to find the solution of larger systems. Okay, so that's the first motivation, that why do we need to learn these different techniques. Okay, that's the motivation, why do we need to learn, because otherwise we will get stuck, or if we have 6 unknowns, method of substitution or Kramer's rule would be very much difficult to apply. Okay, so the first thing we are going to discuss about is matrix inversion. Matrix inversion is not that much convenient, if I uh, say honestly. Matrix inversion is not that much easy, but we will learn about matrix inversion because we can use MATLAB to apply matrix inversion. That's why we are going to learn about matrix inversion first, and then we will discuss about uh, Gaussian elimination. Okay, so we actually will focus on two methods. The first one is the matrix inversion, and the second one is the Gaussian elimination. Are you familiar with Gaussian elimination? Any of you? Uh, yes, I guess some of you might have completed Math 216 already. Yeah, so okay, so in Math 216 in linear algebra part, right? Linear algebra course, I guess you, yes, in Math 216, yes. So in Math 216 linear algebra course, you learned about Gaussian elimination, and Gaussian elimination is a very convenient way to solve system of linear equations. Okay, we will use this Gaussian elimination to solve system of equation. So if you have done Math 216 already, things might become a bit easier to you. But if you haven't done already, no worries. We will go through the topics elaborate, so you don't have to worry about it. Okay, so the first thing first, we will discuss about matrix inversion first. The matrix inversion, the thing that I tried to explain, matrix inversion is convenient using softwares. Okay, like MATLAB. That's why we are going to discuss about matrix inversion. But matrix inversion is that much convenient whenever we have to perform calculations by hand. By hand, matrix inversion is pretty much difficult, honestly. Okay. Uh, if I want to say difficult when doing calculations by hand. So as we are actually focusing on MATLAB, we have a simulation tool with us. So that's why we are going to learn about matrix inversion. Okay, and then we will see Gaussian elimination. Gaussian elimination is easy for both of the cases. Gaussian elimination is easy using MATLAB. We will provide the code, so Gaussian elimination would be easy using MATLAB as well, and Gaussian elimination is easy if we have to perform the calculations by hand as well. Okay. So first things first, matrix inversion. Let's assume we have a system of equation that looks like this. So I will. Okay, so first we are going to discuss about matrix inversion. So this course is actually a bit more about math. Okay, so okay, so first we are going to discuss about matrix inversion. Let's assume we have a system of equation that looks like this. I am going to write the general expressions. Okay, general expression means we have written the system in this way, right? We have the coefficients here 5, we have the coefficient 3 here, -2, then 9, right? We have the coefficient. So we are going to write, instead of these coefficients directly, we are going to write some general terms. Okay, like I can write something like this: a11 x1 plus a12 x2 plus a13 x3 equals to b1. So these are the coefficients, right? So coefficient means if I just copy this equation here, copy the set of equation here. So here the a11 is actually equals to 5. Okay, a11 is equals to 5, a12 is equals to 3, a13 is equals to -2. Okay, and b1 would be equal to 9. So we are actually writing in general form. Instead of specifying specific values, we are going to write the system in a general form. Okay, so we can write the second equation in this manner, that a21, the first number represents that it is the second equation, and the second number represents that this is the coefficient related to the first unknown. Okay, these two represents that this is the coefficient for the second equation, and this one represents that this coefficient is related to x1, the first unknown. Okay, x1 is simply x if we want to make analogy, x2 is simply the y, and x3 is simply the z. Okay. So the first coefficient is a21 x1, then the second coefficient can be a22. So 22 means this is the coefficient for the second equation, and it is related to the second variable, the second unknown. Okay. So x2 plus a23. 23 means for the second equation, 3 means for the third variable, the third unknown, x3 equals to b2. Okay, so similarly we can write the third equation in general form as well if we wish. So we can write a31, the third equation related to the first unknown, then a32, the third equation related to the second unknown, then a33, the third equation related to the third unknown equals to b3. So these b's are the constants, right? So these b1, b2, b3 are these three constants. So we can write any system of equation in this general format. So here is the thing, if we form a matrix using the coefficients of the unknowns, like if we consider a matrix that's formed with a11, then a12, a13, a21, a22. Okay, by the way, in the simulation exams, you may have to write some explanations as well. The key thing you have to do is to simulate and find the solution, but you may have to write some small explanations as well. You will be provided question paper, and in that question paper you will be given some space, so you have to write some sort of small explanations there as well. Like in the question paper, if this is the question, then you will see some space, you may have to write something here. Then the second question, then something to write here. Okay, so you have to submit the question paper after the exam, and also you have to, we will check the solutions by moving on to your computer separately. Okay, okay, we will, হ্যাঁ বল।
স্যার এক্সামের সময়ই তো স্যার পেপারটা দিয়ে দিবেন আমাদের রাফের জন্য এরকম?
হ্যাঁ, কোশ্চেন পেপারটা আপনাদের দিয়ে দিব, আপনারা ওখানে লিখবেন, চিন্তা ভাবনা করবেন, পরে ওটা আবার জমা দিয়ে দিবেন আমাদের।
জি স্যার, জি স্যার।
ঠিক আছে, ওকে ওকে। আর
ওটাতেও কি মার্কস আছে?
হ্যাঁ হ্যাঁ, মার্ক তো থাকবেই, ছোট ছোট কোশ্চেন থাকবে। এই যে ধরেন আমি যে এত কথা বলি প্রতিদিন, তাই না, আমি তো মোটামুটি আপনাদের প্রায় 2, 2.5, 3 ঘন্টা বসায় রাখি, তাই না? এই যে এত কথাবার্তা যে আমরা বলি, এইগুলো একটু ধরেন ওই ছোটখাটো রিলেটেড কোশ্চেন আর, ঠিক আছে?
ওকে স্যার, ওকে স্যার।
খুব কঠিন কিছু যে তা না, এই এক্সপেরিমেন্ট নিয়ে যা যা বলি সেগুলো। ঠিক
জি
আছে,
স্যার।
ওকে 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 ওকে। So we are trying to form a matrix here, a 2 2 and then a 2 3, and the third row would be a 3 1, a 3 2, a 3 3. So we are forming a matrix using the coefficients of the unknowns. Okay, we have the 3 unknowns here, x1, x2 and x3. So using the coefficients we are forming a matrix. Coefficients সহগ, তাই না? সহগ, আমরা x1 x2 x3 যে সহগ গুলো আছে, সহগ গুলো দিয়ে একটা ম্যাট্রিক্স আমরা বানাচ্ছি, coefficients, right? So we call this matrix the coefficient matrix. The name of the matrix is called the coefficient matrix. Okay, সহগ গুলো নিয়ে যে ম্যাট্রিক্সটা বানালাম ওটাকে আমরা coefficient matrix বলি। And the matrix that we form using the constants, like we may form another matrix here using the constants. Constant means this b1, then b2 and b3, and we call these matrix the constant matrix. Okay, constant matrix, or we call it as constant vector as well. Okay, okay, let me write the name as well. If you look carefully, the second matrix is having only one column, right? So we call it the constant vector as well. Whenever we have a matrix having only one column, we may call it as vector as well. Okay, so vector is actually a column matrix. Column matrix means a matrix that has only one column. Okay, so a vector is a special type of matrix. If I want to say vector is a special type of matrix that's called the column matrix, and column matrix is a matrix that having only one column. Okay, something that looks like this. So we may call it constant matrix, we may call it constant vector as well if we wish. Okay, so if we want to write this system of equation with respect to these matrices, then we can write it in this way. I am just going to copy this thing here, and then there would be the unknowns multiplied with this thing to be x1, to be x2, to be x3, and it would be equal to these constant matrix. Okay, so this is the same thing as this. These two are exactly the same things. If you just do the matrix multiplication here, uh, if you can recall the matrix multiplication, what we had to do, we had to take this thing and put it here, x1, x2, x3. Then we are going to multiply them, right? So if I multiply, then I will get a11 x1 plus a12 x2 plus a13 x3 equals to b1, right? So in short, what I'm trying to say is that this is the matrix representation of our system of equation. Okay, so this thing is just an alternate expression. Okay, alternate expression of this system of equation. Okay, so if we want to solve the x1, x2, and x3, what we have to do, we have to perform matrix inversion, right? We have to take the inverse of these metrics. By the way, we may write in simpler notation, like we may write these metrics as a. The coefficient matrix can be written as a. We may write this vector as x, and we can write it as equals to b. Okay, so from here, if we want to find the x vector, we have to perform matrix inversion. Like we have to multiply these matrix A inverse in both sides, right? It would be equals to A inverse B. So we are multiplying A inverse both sides of the equation, and from there we know A inverse A becomes one, or the identity matrix, right? If we take any matrix and take its inversion and multiply them, we get the identity matrix. For any matrix A inverse A, we get the identity matrix, right? Identity matrix looks like this, if you can recall. It was the I matrix. Okay, so and if we multiply any matrix with the identity matrix, we get that matrix. Like if we are multiplying I with x, we get x only. So it would be I. Here we have x, and we have this A inverse B. So multiplying any matrix with the identity matrix results in the same thing. So we will get x from here. X would be equals to this. So here we have to perform the inverse of the coefficient matrix, right? We have to perform the inversion of the coefficient matrix and then multiply with the constant matrix. We have to perform the inversion of the coefficient matrix and simply then multiply it with the constant matrix. And we have to follow the order as well. Like if someone tries to do this thing, B A inverse, it would be wrong. Matrix multiplication is not commutative, right? Commutative means A inverse B will not be equals to B A inverse. This is true for matrix. It might be equal in some special cases, but in general cases, this is not true. That's why you have to follow the order as well. Like you have to multiply A inverse with the B in this order, not in this order. It would be wrong. Okay. So we have to perform the matrix inversion of the coefficient matrix and then multiply it with the constant matrix, and we are done. We will get the value of x. Okay. So and we are not going to find the matrix inversion by hand, as I mentioned that matrix inversion is pretty much difficult whenever we have to find it by hand. We will do this thing using MATLAB. Okay, so let me move on to the MATLAB part here. For inverting any matrix, we have a function in MATLAB called in. Okay. By the way, any query so far? Any queries? Okay. I guess you are okay with the explanations, right? সবকিছু ঠিকঠাক আছে না নাকি না জিনিসপত্র কঠিন হয়ে যাচ্ছে? ঠিক আছে না মোটামুটি?
জি স্যার, বুঝা যাচ্ছে।
Okay, okay. Thank you. Are there any specifications for the x and b vectors? This b vector is called the constant vector. This b is called the constant matrix or the constant vector. The x is actually the vector of the unknowns. Okay, x is also a vector if you look carefully. This is a column matrix as well. So we may call the x as the vector of the unknowns, the unknown vector. Okay, a is called the coefficient matrix. This is the a is called the coefficient matrix and b is called the constant matrix. We can call x the unknown vector or unknown matrix if you wish. Okay, so now we want to move on to the MATLAB. By the way, I should start my MATLAB. It might take some time. Okay, so the thing that I was trying to say, we have a function named in MATLAB, a predefined function that can calculate the inverse of any matrix. Okay, we have a function called inv. So if we just write something like this in a, then we will get this a inverse. Okay, so let's try to solve this system of equation. Let's assume we have this system with us and we have to find the value of x, y, and z. X, y, and z. Okay, so if we have this system with us, then we can form the a and b matrices first. What would be the a matrix? The a matrix would be 5 3 -2, then -2 -5 9 1 -2 5, right? So this is the coefficient matrix, and for the b matrix we will have what? For the b matrix we will have
স্যার
হ্যাঁ বলেন।
স্যার এক্সামে কি এরকম ভাবে দিবে নাকি 5/2x এরকম থাকবে স্যার? এগুলা এরকম একটা করালে ভালো হতো।
আরেকবার একটু বলেন।
স্যার এক্সামে যেমন এরকম 5x + 3y - 2z মানে একটা সহজ একটা ইকুয়েশন এক্সপ্রেশনটা দেওয়া আছে, কিন্তু স্যার এক্সামে দিয়ে দেয় যে 5a/2b এরকম +3a/4b এরকম থাকে অনেক সময় স্যার, ওই রকম যদি করানো হতো।
5a/2 বলতে আমি ঠিক বুঝি নাই, মানে মনে করেন 5।
স্যার আমি লিখে দেখাচ্ছি স্যার একটু
আচ্ছা
দাঁড়ান।
আচ্ছা আচ্ছা, ঠিক আছে, একটু লিখে দেন। ওকে, এক্সামে একটু কঠিনই থাকবে, এক্সামে এত সোজা থাকবে না। ধরেন এক্সামে আপনাদের একটা সার্কিট দিয়ে দিলাম, হ্যাঁ ধরেন একটা এসি সার্কিট দিয়ে দিলাম, আবার এসি সার্কিট নিয়ে আমি অনেক ঝামেলা করি। এসি সার্কিট দিয়ে ওইখান থেকে হয়তো ইকুয়েশন খুঁজে বার করতে বলা যায়, ওখানে হয়তো ইকুয়েশন খুঁজে বার করা লাগবে না। আপনারা নোডাল অ্যানালাইসিস, মেশ অ্যানালাইসিস করেছেন না? ধরেন ওরকম একটা নোড মেশের টাইপের রিলেটেড প্রবলেম দিয়ে দিলাম, ওখান থেকে সেট অফ ইকুয়েশনটা খুঁজে বার করতে হবে, খুঁজে বের করে তারপর ওটা সলভ করতে হবে, এরকমও হতে পারে। ঠিক আছে, সো ইন এক্সামস you may have you may have to do some other thing as well, like in exam you will not see, you may not see, you will get this type of equations as well, but there is a probability that the question might become okay. So in case of exam you will have to make the system of equations first. You may not get this system readily. You will be given a scenario, and from that scenario
there might be KVL or KCL equation, right sir?
Exactly. So let's assume for it might be true for circuit cases, but the scenario could be different as well. Okay, so if we consider from the circuit perspective, let's assume I have given you a simple DC circuit. Let's just skip the AC. So let's assume we have a circuit that has 3 loops. Okay, we have a current source here. So in these 3 loops, you will get 3 unknowns, right? If we consider this is the I1, this is I2, this is I3, you have 3 unknowns. The first thing you have to do, you may have to, I'm not saying that we will give this type of problems, but just I'm trying to give you an idea. We will discuss about this type of problems in the next session, in the next Friday. Okay, so we will discuss about some relevant problems. So from there, first you have to make a system of equation of these I1, I2, I3. Then you have to solve the system using MATLAB or using the Gaussian elimination, this sort of thing. Okay, it could be one case, or you may be given a stem, a paragraph. So I have given you a stem or a paragraph. I guess you are familiar with the creative question, সৃজনশীল, তাই না? আপনারা সৃজনশীল পদ্ধতিতে পড়ালেখা করে আসছেন না? আসছেন তো, আই গেস আপনারা তো পেয়েছেন ওগুলো, তাই না নাকি?
ইয়েস স্যার,
হ্যাঁ
ক্রিয়েটিভ কোশ্চেন। স্যার আমি একটা প্রবলেম দিছি স্যার, এইরকম ইকুয়েশন গুলাকে কিভাবে সলভ করব স্যার?
এখানে কি আপনার এ বি গুলো আননোন?
জি স্যার।
আপনি 1/a টাকে ইয়ে ধরে, আচ্ছা আননোন কোনগুলো, এ বি না এক্স ওয়াই?
স্যার এ বি আননোন, এক্স ওয়াই কে আমরা বের করব স্যার, এক্স ওয়াই এর ভ্যালুটা বের করব স্যার।
আচ্ছা, এক্স ওয়াই এর ভ্যালু বের করবেন। 1/a কে আপনি ডিরেক্ট ম্যাটল্যাবে বসিয়ে দিতে পারবেন, সমস্যা নাই তো। আপনি ম্যাটল্যাবে 1/a কে ডিরেক্টলি বসিয়ে দিবেন, সমস্যা নাই, ঠিক আছে?
ওকে, জি স্যার, জি স্যার।
ওকে ওকে। So one other different type of problem might be this, that you will be given a stem, a paragraph, and from that paragraph you have to make the system of equation first. Okay, you have to find the system of equation by reading this paragraph, then you have to solve the system. Okay, যে আপনাদের একটা ওরকম একটা প্যারাগ্রাফ মতন দিয়ে দিলাম, একটা অনুচ্ছেদ দিয়ে দিলাম, ওখান থেকে পড়ে আপনাকে আগে সিস্টেমটা বানাইতে হবে, যে x1 x2 x3 কি কি আননোন ওখানে আছে, আননোন গুলো আগে খুঁজে বের করতে হবে, খুঁজে বের করে একটা সিস্টেম বানাতে হবে, তারপর ওটাকে সলভ করতে হবে।
স্যার দুই একটা যদি প্র্যাকটিস প্রবলেম দিয়ে দিতেন স্যার এরকম।
হ্যাঁ হ্যাঁ, আমরা করব, আমরা ওই যে নেক্সট ফ্রাইডে থেকে আমরা করব।
ওকে
ঠিক আছে, আমরা যে 3টা এক্সপেরিমেন্ট করেছি 1 2 3, ওই 3টার উপর আমরা নেক্সট ফ্রাইডেতে করব, ঠিক আছে? আর আপনাদের ল্যাব শিটের প্রবলেম গুলো আপনারা সলভ করবেন, অবশ্যই অবশ্যই সলভ করবেন, ল্যাব শিটের প্রবলেম গুলো, কোড গুলো, ওগুলো করবেন, আর আমরা প্রবলেম সলভিং সেশন করব। ওকে, okay, so now we want to solve the value of the xyz from here, right? The xyz from here. Okay, so I will try to continue the whole class solely in English. Okay, but sometimes I might explain something in Bengali as well. If I find something that's important to explain in Bengali, I might explain something in Bengali as well. Okay, but I am explaining all the things in English so that you don't miss any important topics if you are a foreign student. Okay, so no worries. I won't explain something in only in Bengali that you will miss out. Okay, okay. Thank you. So okay, I should share my whole screen with you as I want to solve the problem using MATLAB. I'm going to stop share this screen. Share the whole screen now. Okay, I guess my whole screen is visible now. So what we have to do first, we have to make these 2 vectors or 2 matrices, right? So we may create a new script. We may write that we write generally. Then for the A matrix, we are going to specify this matrix, right? 5 3 minus 2, this is the first row. So if you can recall, we discussed in detail about the matrices in the first sessions, right? In the first 2 sessions, we discussed about some general things about MATLAB. There we covered the matrix part, matrix and array part. So we are going to define this matrix first. So the first row is 5, 3, minus 2. So we have 5, then comma, then 3, then minus 2, and then we have to define the second row. For defining second row, we have to put semicolon. Okay. So after putting commas, we are going to put semicolon to make MATLAB understand that we are defining a new row now. Okay, so the new row would be minus 2, minus 5, 9, minus 2, minus 5, 9, then put a semicolon once again for the third row. For the third row, we have 1, minus 2, 5. Okay, so it would be 1, oh, sorry, 1, minus 2, 5. So this is the coefficient matrix. And for the constant matrix, can anyone say how should I write this constant matrix? We have 9, minus 5, and minus 6. They are in column format. Okay, they are in column format. So can anyone say how should I write this B matrix in MATLAB? We have 9, minus 5, and 6.
Sir, can we go 9, then semicolon, minus 1?
Exactly, exactly. Thank you. So that's what I was expecting. So this is a column matrix, right? So the first row consists only one element. The first row consists of only one element. So after writing 9, we are going to put a semicolon because we want to move on to the second row. The second row consists of minus 5, and then the third row is of minus 6. So 9, minus 5, then minus 6. So this is the B vector, the B matrix or B vector. And if we want to find the value of the unknowns x, we have to first take the inverse of A. And for taking the inverse, we are going to use this function, int function. Okay, this int function is a predefined function or pre-written function. So MATLAB provides us with this function readily, and then we are going to multiply it with this B. Okay, A inverse B, and then we can write or we can display this x. So if I just run this code, where I'm going to say this code. Okay, so let me write it. Save matinf. So here are the roots we have. Okay, minus 27.5, 70.5, and 32.5. We may go for larger system of equation as well. Let's assume we may have 4 unknowns. Then from that 4 unknowns, we first have to find the coefficient matrix and also the constant matrix. Then we can find the value of the unknowns x using the matrix inversion. One thing that I should discuss with you, I guess most of you have completed triple 203 already, but some of you are doing triple 203 this semester. MATLAB can deal with complex coefficients as well. Okay, MATLAB can deal with complex coefficients as well. So let's assume you have got a system, or after performing KVL, KCL, or mesh analysis or nodal analysis, let's assume we have got, okay, let's try to solve a system of equation that we have already. KVL, KCL. We need something with IJ. Mm, I guess we consider the phasors here only, right? Okay, let's assume we have a system of equation that looks like this. MATLAB can deal with complex coefficients as well. So let's assume we have 5 plus twice j I1, then minus 2 minus 3j I2 plus 5 I3. It's equals 2 minus 10j. This is the first equation. After doing mesh analysis, let's assume we have got this thing. Okay. For the second equation, this is 2I1 minus 3 minus 2j. Let's make it plus I2, then 3 minus 2j I3 equals to 2, and minus 5 plus 6j I1 plus 3 plus 5j I2. This is 3I3 equals to minus 9. Okay, so you can put the coefficients in MATLAB in complex format as well. Okay, so for MATLAB to understand the j portion, you can use either j or you can use I if you wish. Like if I write 5 plus 2I, then MATLAB will understand that this is the imaginary portion. The 5 is the real portion here, and this is the imaginary portion. Okay, so you can put the coefficient in complex format as well, and MATLAB can solve complex equations. MATLAB takes complex coefficients as well. It can solve complex. So in case of triple E 203 or any complex equation, you can verify it with MATLAB if you wish, because our calculators cannot find the solutions for complex equations, right? Our calculators can only find solutions having real coefficients. But you can do this thing using MATLAB if you wish. So here the first row will be 5 plus 2I, then 2 minus 3I, and 5. So you have to write these things here. 5 plus 2I, then the second coefficient is what? 2 minus 3I. 2 minus 3I, and the third coefficient is 5, right? This is 5, and the constant is 2 minus 10j. So it would be 5, and the constant is 2 minus 10. Okay, so you can define the whole equation in this way after getting the coefficients, and then MATLAB will solve you the value of the three mesh currents, the I1, I2, and I3. Okay, you can verify your calculations using MATLAB. Okay, so that's the thing about matrix inversion. We will now move on to the second part, and this part is our main focus because the Gaussian elimination. Yes, inquiries. Yes, it can deal with phasors too, but I have to recall how we can represent a phasor in MATLAB. Please do some Google search. MATLAB can deal with phasors as well, like the value of the magnitude and the angle, the phasor format. MATLAB can deal with phasors as well. Okay, let me have a look here. MATLAB can deal with phasors as well, but I cannot recall how to do that. Okay, you can have a look how to represent a complex number in phasor in MATLAB. I guess it can be done as well. I cannot recall right now. Okay, I will have a look as well. I will have the angle parameter here, magnitude parameter here. Okay, I will have a look and I will let you know. Okay, you can have a look as well. Okay, okay, thank you. So, but MATLAB can deal with it as far as I can recall. Now we will move on to the second part of our discussion, and this is of the main focus for today, because matrix inversion is not, we don't have to do much here, but we have to do something in Gaussian elimination. So our main focus would be on this portion. Okay, Gaussian elimination. Okay, let me share my screen once again. So if you have any queries so far, you can share. Okay, feel free to share any queries you have. So now we will discuss about Gaussian elimination. Okay, so what Gaussian elimination? So first thing first, the motivation of Gaussian elimination. Why do we need Gaussian elimination? So these small things that I try to explain is important for the exam that I talked about, that you will face or you will be given some small questions like why do we use these numerical techniques, or why do you choose interpolation over regression, or why do you choose regression over interpolation, or why are you going to choose Gaussian elimination to solve a system of equation instead of substitution method or elimination method or Cramer's rule. Okay, so you may have to think about these answers. Okay, so first thing first, why do we need Gaussian elimination? We know about these techniques, we know about matrix inversion. Why do we need Gaussian elimination now? Okay, so matrix inversion is a very time consuming method, if I want to say. Whenever the system becomes large, matrix inversion is not efficient. Okay, uh, when the system becomes large, matrix inversion is a very time consuming in these cases. Okay, time consuming means in MATLAB will if I want to say, sometimes struggle to find the value, or MATLAB will take some time. Like in the previous case, as I just hit the run button, MATLAB provided the solution, right? But in some cases, you if you have a large system of equation, like if your coefficient matrix is a 6 by 6 matrix and you are trying to find the inverse of A, then you will see MATLAB will take some time to get the value of the inverse of A. Okay, when the system is small, you will not be able to distinguish between the methods, the Gaussian elimination or the matrix inversion. But when the system becomes large, matrix inversion is a very time consuming technique. Okay, and it is also difficult for our hand calculation as well. And MATLAB will struggle when the system becomes large. You can try yourself. You can do some experiment. Find a large system of equation having 6 unknowns, 7 unknowns, and then try to solve it using MATLAB. You will see that MATLAB is taking some time. Okay. Yes. Whenever I'm saying that system, I am trying to say system or system of equation. Whenever I am uttering this word system or system of equation, I am trying to mean that we have a large number of unknowns. Okay, I am trying to mean greater number of unknowns. Okay, so large system means we have 6 unknowns, 7 unknowns, this type of things. Okay, system means the system of equation. System of equation becomes large means we have greater number of unknowns. Okay, okay, thank you for your queries. So I will suggest everyone to ask queries, so that everything becomes clear to you. Okay, so please ask more questions. Thank you for your queries. So the bottom line is matrix inversion is not that much efficient technique. It is easier to implement in MATLAB, but it is not that much efficient. Okay, so in those cases, Gaussian elimination can help us. Gaussian elimination is a technique that solves the system in an alternate way, and it will help us to find the solution of larger systems in less time. Okay, so when we have a large system, it means we have a greater number of unknowns. Gaussian elimination will help us to find the solution in less time. Okay, it is more efficient for solving a system using any software. Okay, so how do we solve a system using Gaussian elimination? So let's assume we have the system as this. We are considering a system having 3 unknowns. So I'm going to copy this thing. So let's assume we have these. I'm going to explain with a small system, but this is applicable for larger systems as well. I am going to explain it with a system having 3 unknowns, but it is applicable for larger systems as well. Our code will remain same and code will run for larger systems. And we have the constant and coefficient matrix like this. I'm just going to copy this thing as well. And we want to find the value of the unknowns using Gaussian elimination. Okay, so Gaussian elimination, by the way, the way that you used Gaussian elimination in Math 216, we may use Gaussian elimination in a bit different way for our case. Okay, so in Math 216 you actually dealt with matrices, right? You actually solve the system directly using this type of matrices. But in case of this course, I will try to explain it in a bit different way. The core things are the same. The core things are exactly the same, but for our coding perspective, like the way we are going to implement Gaussian elimination in code, I'm going to explain it in a bit different. The code things are same, but I'm going to explain it in a bit different way so that it becomes yes. Any queries? I guess some of you raised hand. Any queries? Okay. 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 So the core things will be the same, but I will try to explain it in a different way so that it becomes easier for us to understand the code. Okay. So the idea of Gaussian elimination or the approaches of Gaussian elimination consists of two steps. The first step is called the forward elimination. It's called the forward elimination. And step 2 is called the backward substitution. Okay, these are the two steps we are going to follow for Gaussian elimination. Okay, the forward elimination is exactly the same as you have done in Math 216. If some of you have done in Math 216, just I'm going to explain it in different way. So the name, as the name suggests, forward elimination. Okay, so for forward elimination, as we have three equations here. So first we are going to discuss about forward elimination. Okay, so as we have these three equations, the first equation will be considered as the pivot equation. Okay, for the first case, we will call the first equation as the pivot equation. The first equation, so this is equation number one. Let's try to give numbers to this equation. So this is equation number one. I will try to explain the theory first, then I will move on to the code. Okay, after explaining the theory, we will take a break of, I guess, 5 or 10 minutes, then we will move on to the code. No worries. So for the first case, we will call the first equation as the pivot equation. Pivot actually means the center, if I want to say center, or something around which everything rotates. Okay, পিভট মানে হচ্ছে, যদি আমি সহজভাবে বলি, পিভটের সহজ বাংলা মানে হচ্ছে কেন্দ্র টাইপের কিছু একটা। হ্যাঁ, কেন্দ্র মানে হচ্ছে, পিভট কোনগুলোকে বলে জানেন? ওই যে দরজা থাকে না, দরজায় আমাদের যে কবজাগুলো থাকে, ওই জায়গাগুলোকে পিভট বলা হয়। ওকে, সো a pivot is a thing around which something can rotate. So the doors that we have some portion here, and around, okay, let me try to draw a door.
মানে যেটাকে কেন্দ্র করে আর কি এটা মানে রোটেট করে এরকম কিছু।
Exactly, যেটাকে কেন্দ্র করে আসলে রোটেট করে। So let's assume if this is a door we have, so this door can move in this way or in this way. So this is the pivot. This part would be the pivot. This is the fixed portion, right? This is the fixed portion, and using this fixed portion, this door can rotate in this way, or this door can rotate in this way. Here are some nuts and bolts, right? And these nuts and bolts remains fixed, and in Bengali we call this something called কবজা or nut bolt, যেগুলো আমরা বলি। হ্যাঁ, ওই কবজাগুলোর রেসপেক্টে ঘুরে না, এইগুলোকে আমরা আসলে পিভট বলি। The thing that remains fixed is actually called a pivot. Okay, so this part remains fixed. We have some nut bolts, and the door can move around this portion. So in general, if you want to say, pivot is something that's called the center of anything. Okay, so the first equation is called the pivot equation because we will consider this equation as the center. We will keep the first equation unchanged, and considering this equation, we will eliminate other terms. We will make other terms zero. Okay, so we are calling the first equation as the pivot equation because this equation will remain unchanged. It will remain fixed, and considering this equation, we will eliminate other terms. It would be the center, and we will eliminate other terms considering this first equation. Okay, so that's why we are calling it the pivot equation. And after deciding about the pivot equation, we decide about the pivot element. So for each of the equation, the diagonal elements are the pivot elements. Okay, so in this first equation, this A11 is the pivot element, and at some step we will consider the second equation as the pivot equation, and then we will see that this A22 would be considered as the pivot element. Okay, we will move on to the second part later. Just for now, we are considering the first equation as the pivot equation, and we know about the diagonal, right? Diagonal means কর্ণ বরাবর যে এলিমেন্ট গুলো থাকে এই বরাবর, these are the diagonal elements, right? These are the diagonal elements. So the elements that are in the diagonal, if I look at the matrix, these elements are in the diagonal, right? These elements would be considered as the pivot element.
স্যার
হ্যাঁ,
A13 A22 A31 এটা তো ডায়াগোনাল।
A13 A22 A31. Acha, so we can be more precise. We are focusing on the principal diagonal. Okay, we are not going to consider this diagonal. Okay, we are focusing on the principal diagonal, the diagonal that we generally understand by. Okay, this is called the principal diagonal. This diagonal is called the principal diagonal. আমরা প্রিন্সিপাল ডায়াগোনালি চিন্তা করব, এই দিক বরাবর যেটা আছে সেটাকে চিন্তা করব না। We are not going to consider this diagonal. Okay, so after fixing about the pivot equation, we are thinking about the pivot element, and as our pivot equation is now the first equation, our pivot element is this. So this is our pivot element. This is called the pivot element. So why we are calling it the pivot element? Because by focusing on it, keeping it as the center, we are going to eliminate these two terms. We will make these two terms zero. As the name suggests, we are going to eliminate something, right? Forward elimination. Why we are calling it forward elimination, I will explain the word forward later. But for now, just try to understand that we are going to eliminate some terms. By the term eliminate, I want to mean that we are going to make the term zero. Okay, by using the word elimination, I am trying to mean that making some terms zero, eliminate them, just kill them. That's it. Zero. Okay, so considering this pivot element A11, we are going to eliminate these two terms, the terms that's below the pivot element. A21 and A31 are below A11, so we are going to make them zero. So how we are going to make them zero? Let's first focus on A21 only. Okay, so the general rule is, or the thing that we have to do, first take the pivot equation, then multiply it with the take the pivot equation, divide it with by the pivot element, and multiply it by the term that you are trying to eliminate. Okay, let me repeat once again.
Sir, pivot element বলতে কি বোঝাচ্ছেন?
আরেকবার একটু বলেন কাইন্ডলি।
Sir, pivot element actually.
পিভট এলিমেন্ট বলতে কি বুঝি?
মানে এটা স্যার, মানে এটা কি পিভট এলিমেন্ট স্যার? এটা বুঝতে পারছি।
আচ্ছা, মানে পিভট এলিমেন্ট আমরা এটাকে বলতেছি তার কারণ হচ্ছে যে এই এলিমেন্টটাকে ফোকাস করে আমরা এই নিচের এলিমেন্ট গুলোকে এলিমিনেট করব আর কি, জিরো করব। হ্যাঁ, এই জন্য এটাকে পিভট বলতেছি। আর পিভট এলিমেন্ট গুলো,
স্যার পিভট বলতেছি, স্যার পিভট বুঝতে পারছি আমি অ্যাকচুয়ালি। স্যার র‍্যাঙ্ক যখন অ্যাকচুয়ালি বের করি তখন পিভট বের করে ম্যাট্রিক্স, এটা বুঝতে পারছি। বাট স্যার এই যে পিভট এলিমেন্ট বলতে কি বুঝাচ্ছেন ওটা বুঝিনি।
আচ্ছা, পিভট এলিমেন্ট বলতে অনলি দিস টার্ম, অনলি A11। ঠিক আছে, এই পুরোটা তো আমাদের পিভট ইকুয়েশন, তাই না? এই পিভট ইকুয়েশন দেখেন আমাদের চারটা টার্ম আছে, চারটা যদি আমি বলতে চারটা না অনেকগুলো টার্মই আছে, জাস্ট a11 টাকে আমরা পিভট এলিমেন্ট বলতেছি।
ওকে স্যার, বুঝলাম যে কনস্ট্যান্টটা অ্যাকচুয়ালি হচ্ছে যে ফার্স্ট a11 এর সাথে মানে x1 এর সাথে যেটা থাকবে ওইটাই।
এক্স্যাক্টলি x1 এর সাথে যেই
Okay.
সহগটা থাকে এই কোএফিসিয়েন্ট সেটাকে আমরা পিভট এলিমেন্ট, ঠিক আছে? এই যে the
ওকে স্যার,
diagonal coefficients actually. First we will consider
বুঝতে পারছি।
okay. Thank you. So for the forward elimination, the general step is take the pivot equation. We are taking the equation number 1, divide it by the pivot element, divide it by a11, and multiply it with the coefficient that you are going to eliminate. So we are trying to eliminate this term. We are going to make this term 0. So that's why we are multiplying it with a21. Okay, that's the first step. So if we do this thing, what do we get? Let me write this thing. So if we do this calculation, the number one equation will get changed. We will get something like this. We have a11, it would be multiplied with this thing, x1. Okay, let me write this thing. So let's assume we're multiplying each of the terms with this. So we have the a11 x1, then the second term would be this. We are going to multiply it with a12 x2. Okay, it would be multiplied with a12 x2. Then the third term would be this, a13 x3. Okay, let me delete these things for now. And the third term and the constant term would be this, times b1, right? So I have multiplied these coefficient with each of the terms of equation 1. Okay, so what we can see here that these a11 terms would be cancelled out here at the for the leftmost term. It would be cancelled out. We will get what? We will get a21 x1. That's the thing we are focusing on. And let's consider this coefficient and name it a12 prime, a12 prime x2. Then consider this coefficient and name it as a13 prime x3, and consider this coefficient as b1 prime. Okay, so what we can see from here that the first term has these coefficient now a21 x1, and we are considering this coefficient as a12 prime. Okay, and we are considering this coefficient as a13 prime. If we consider this coefficient, we are considering it as a13 prime, and we are considering this coefficient as b1 prime. So we may consider this equation as 1 prime equation. Okay, this is the 1 prime equation. So now what I have to do, our target was to eliminate this term, right? Our target was to eliminate this term. So if I just now subtract this 1 prime equation from 2, then this term would be eliminated. Okay, let me copy this equation. So this is equation number 2, and in this equation number 2 we were supposed to eliminate this term, and we have this 1 prime equation here, So if I just subtract 1 prime from 2, let me make it a bit smaller. So if I just subtract 1 prime from 2, then what I'm going to get from here, these two terms would be cancelled out, and then we will have a 2 2 minus a 1 2 prime x2, considering these two terms, a 2 2 minus a 1 2 prime x2, and we will have a 2 3 minus a 1 3 prime x3, considering these two terms, and considering the constants, we will have b2 minus b1 prime. Okay, so I'm going to rename the coefficients once again. I'm going to name it as a 2 2 prime x2. I'm going to name it as a 2 3 prime x3. By calculating this result, I'm writing it as a 2 2 prime. Okay, and by calculating this result, I'm writing as a 2 3 prime, and we will get b2 prime here, and we can name it as 2 prime equation. Okay, so what have we done so far? We had this system of equation. Let me copy this here. We had this system of equation, and instead of this equation number 2, we are going to use this 2 prime equation now, because we have eliminated this term from here. Okay, so I'm going to remove this equation, and we are going to use this 2 prime equation now. So I'm going to paste it here. Okay, so this is the 2 prime equation we have now, and we will keep the third equation unchanged for now. We will focus on the third equation in the next step. So it was our third equation. So we can now easily see that this term has been eliminated. This is a big zero now. Nothing is present here, right? So just have a look once again. What did we do to eliminate this term? What did we do to make this term zero? The first thing, we took the pivot equation, we divide the equation by the pivot element, and we multiplied it with the term that we want to eliminate. We wanted to eliminate this term. That's why we multiplied with this coefficient. And then we got the modified equation, modified pivot equation. We may name it as our modified pivot equation for now. This 1 prime is the modified pivot equation. This is the first step, and in the second step, as we wanted to eliminate this term in the second equation, we subtracted the modified pivot equation from the second equation. Okay, it was the second equation. We subtracted it. We subtracted the modified pivot equation. That's how we actually eliminated this term. This is the general step. So now we are going to eliminate this term, and you will help me how we can eliminate it. So now we want to eliminate this term. The pivot equation is number 1 equation still, because this a31 is below a11. Okay, so This is our pivot equation still. This is our pivot element still. So how we are going to eliminate A31? Can anyone suggest? Take the pivot equation. What should we divide it by and what are going to multiply it with? কি দিয়ে ভাগ করব কি দিয়ে গুণ করব বলেন তো?
Sir, 131 দিয়ে গুণ দিব 11 দিয়ে ভাগ দিব।
Exactly. So we are going to divide it by the pivot element, the A11, and we are going to multiply it with the element that we want to eliminate. We want to eliminate this thing, so we are going to multiply it A31. So then what we will get, okay, let me write it in detail in fast way. I have to write faster. So we will get this thing, paste it here, then A11 x1 plus this thing, it would be multiply it A12 x2 plus we will have this thing, it would be multiplied with what, A13 x3, and the constant term would be multiplied with the same thing we have into B1, right? So in the same way, these two coefficients would be cancelled out. A11 would be cancelled out. We will have the A31 x1, that's the focus here. A31 x1. Then we have the second term. Let me write it in compact form. We are going to consider this coefficient as A12 double prime, let's assume. A12 double prime x2, and then we are going to consider this coefficient as A13 double prime. X3, and then we are going to consider the constant as B1 double prime, and we are going to name it as 1 double prime equation. Okay, so this is the modified pivot equation now. Okay, so the second step was subtract. So we have the third equation, this. Let's copy the equation here. We have the third equation, looks like this. We have the modified equation that looks like this. Now we are going to simply subtract one equation from the other. Okay, so we are going to subtract the 1 double prime equation from equation 3. So if we do this, it would be cancelled out, and we will have A32 minus A12 double prime x2, and we have A33 minus A13 double prime x3 equals to B3 minus B1 double prime. So we are going to rename the coefficients. I can write it as A32 prime x2 plus I can write it as A33 prime x3 equals to B3 prime, and we are going to name it as 3 prime equation. Okay, so our system was previously this. Our system was previously this. So we are going to take the first two equations, and the third equation was this. It was the third equation, but we are not going to consider this third equation. Instead of this, we are going to consider the 3' equation. Okay, so I'm deleting this. We are going to consider this 3'. Okay, let me make it small. So now I guess you can see we have eliminated the term that we wanted to, right? We have two big zeros now below this A11 term, right? This pivot element, below this pivot element, we have two zeros here. We have eliminated these two terms. Okay, we have to eliminate one more term because we want to make a matrix that looks like the upper triangular matrix. Okay, we will discuss about the upper triangular matrix. So by performing forward elimination, we want to make a matrix that looks like this. Initially we had this thing, and after the forward elimination step we expect to have this type of thing. Two zeros here, so we want to form a matrix that look like this. We call it upper triangular matrix. Okay, so after performing the forward elimination, we expect to get this type of matrix. Okay, all the elements below the diagonal would be zero. We call it upper triangular matrix. Because all the elements below the diagonal, this is the diagonal, right? This is our diagonal. So all the elements below the diagonal is zero, right? Here we have two zeros, here we have 1 0, right? All the elements below the diagonal is zero. That's why this matrix is called upper triangular matrix. And by performing forward elimination, we wish to make this type of matrix. So now if I just look at our matrix, in our matrix we have make this term zero, but we are left, or we still have to eliminate this term. We have to eliminate one more term, right? So we are going to eliminate this term as well. Okay, okay, so what should we do to eliminate this term? Now we will consider this 2' equation as our pivot equation. Okay, so to eliminate this term, as I mentioned, the pivot elements will always be the diagonal elements, right? The pivot elements will always be the diagonal elements. So these A32' is below these diagonal elements, right? A22'. So now this 2' equation would be our pivot equation. And these element would be considered as now our pivot element. Okay, so we will follow the same step, and we want to eliminate this term now, A32'. We are going to eliminate this term, A32'. Okay, so we will follow exactly the same step. We are actually doing the things repeatedly. Repeatedly doing things help us to implement in code. Okay, if you have got some sort of pattern, then it is easier to write code. Okay, so for writing any code, we actually have to generalize things, or we have to make things do in a certain pattern, in those cases we can write a code easily. That's why I'm trying to explain this thing in this way. Okay. So we will do the same thing. What? Take the pivot equation. Now the pivot equation is 2 prime. Multiply it with the term that you want to eliminate. So we want to eliminate what? We want to eliminate a32 prime. So multiply it with a32 prime. Divide it with by the pivot element a22 prime, and let's see what happens. So what will happen now? So like, let's take this coefficient. I have to write faster. So we are going to a22 prime x2 plus a23 prime x3, and the constant term would be multiplied as well into b2 prime, right? So here similarly these coefficient gets cancelled out. So we are doing things in pattern. It's nothing, no difficult thing we are doing here. A32 prime x2 plus, let's consider this coefficient as a23 double prime. So a23 double prime x3, it would be equal to what? Let's consider this coefficient as b2 double prime. Okay. b2 double prime, and we can name this equation as 2 double prime. So the second step was yes, an is okay. So okay, you can leave. You can give your attendance and then you can leave. Okay, no worries. You can give your attendance and then you can leave. Okay, so now we are going to do the same step. We will subtract this modified pivot equation, which was our modified pivot equation.
Just sir, we can write our ID name. All right, sir.
Just ID দিলেই হবে. Okay, so we are going to subtract these 2 double prime equations from this 3 prime. So if I do this thing, this is the 3 prime equation. We are going to subtract this 2 double prime equation from here. So the first term would be cancelled out, this term would be cancelled out, and we will have only one term left. That's the a33 prime minus a23 double prime with x3, and the constant would be b3 prime minus b2 double prime. So we can rename, we can write this coefficient as a33 double prime x3. It would be equals to b3 double prime. We can name this equation as 3 double prime. So now we have performed our forward elimination. So previously this was our system of equation. So it was our system of equation, and we have modified the third equation. So now we will consider this third equation instead of this. So I'm going to delete this thing. So we are going to use this third equation as our. So now we can see we have performed the forward elimination, right? We have the zeros here. We have a 0 here. We have a 0 here. We have a 0 here, and we have a 0 here as well. Okay, so we have performed the forward elimination step, and then we will move on to the backward substitution. Backward substitution is pretty much easy. easy to understand for
Sir,
হ্যাঁ বলেন
I have a question, sir.
হ্যাঁ বলেন sure.
Sir, in next class, it would be Saturday or Friday?
In Friday, hopefully we will arrange a problem solving session, and in Saturday you will the first simulation exam will be arranged.
Okay, sir. মানে টাইমটা কতক্ষণ? How much time?
Time খুব বেশিক্ষণ লাগবে না হয়তো। The time for the exam, I guess you may have to solve 2 problems, so the time for the exam would be 40 minutes or 50 minutes.
Okay, sir. Okay, sir. এটা
তো
তো
এক্সামটা কি নেক্সট স্যাটারডে?
Next Saturday, first simulation exam. মানে ওই যদি আমরা দুইটা ভাগে ভাগ করে দিই, তো প্রথমটা দিয়ে দেন, পরেরটা শেষের দিকে দিলে তাহলে ভালো হবে।
স্যার মানে কত মার্কস ক্যারি করবে এই সিমুলেশন টেস্টে?
সিমুলেশন টেস্টে বেশ ভালো মার্ক ক্যারি করবে। ফর দ্য as you will have 2 problems, so 20 marks, and for the second simulation exam it would carry 20 marks, so these 40 marks would be directly added to the total 100.
Yes, sir. Yes.
Okay, so
Okay,
20
sir. Thank you.
20
স্যার
20
কাইন্ডলি অ্যাকচুয়ালি স্যার ক্লাসরুমটা পোস্ট করে দিন ভালো হয় স্যার।
আরেকবার একটু বলেন, আমি বুঝিনি।
মানে স্যার ক্লাসরুমে স্যার যে নেক্সট ইয়ার হচ্ছে সিমুলেশন এক্সাম এটা নিয়ে স্যার একটু পোস্ট করে দিলে ভালো হয়।
আচ্ছা আমি আজকে অ্যানাউন্স করে দিই।
স্যার এটা কি স্যার আমরা গ্রুপ ওয়াইজ দিব নাকি
না
ইন্ডিভিজুয়াল?
না ইন্ডিভিজুয়াল, গ্রুপ ওয়াইজ আর কিছুই না, শুধু আপনার রিপোর্টই গ্রুপ ওয়াইজ, আর কিছুই
জি স্যার। ওকে স্যার।
ঠিক আছে, গ্রুপ ওয়াইজ পরীক্ষা দিবেন, কি ভাই?
জি স্যার।
কি যাই হোক, আচ্ছা, so the simulation exam would be individual. I will post the details on Google Classroom tonight. Okay? No worries, I will post the details.
Thank you, sir.
Okay, thank you. So we have performed the forward elimination step. We have done it already. Okay, so forward elimination is done. Now we will move on to the backward substitution. Forward elimination is done. Okay, done. Now we will move on to backward substitution. So we call it the forward elimination because in the first equation we have all the coefficients unchanged. Okay? Forward means x1, then x2, then x3. So if you look carefully in the first equation, all the 3 unknowns are present, x1, x2, and x3. Then in the second equation we have only x2 and x3, so we have eliminated x1. Okay, so we have eliminated x1 for the second equation, and for the third equation we have eliminated x1 and x2. So in the forward manner we have eliminated x1 first, and then we have eliminated x1, x2 in the forward manner. Now for the second step, backward substitution, we will do in the opposite way. Okay, so step 2 is backward substitution. We will find the value. Okay, by the way, by having a look at this system of equation, can anyone guess which variable is easier to find, x1, x2, or x3?
স্যার x3
exactly. So by having a overall look, by having a simple observation, we can easily see that the x3 can be found first, right? So that's why we are calling it backward substitution. Why we call it substitution, we will see the meaning of substitution as well. We will first find x3, then we will find x2, and then we will find x1. So we are moving in a backward manner. That's why it's called backward, and we will know why it's called substitution. So forward elimination was called forward because we first eliminated x1 here, then we eliminated x1 and x2 in the forward manner. and now we will move on to the backward manner. Okay, so we can find the value of x3 in a pretty easier way. We have, if we consider the 3' equation, considering this 3' equation, if we consider this, x3 can be found simply by making this b3 double prime divided by a3 double prime, right? We can easily find the value of x3. Solved, x3 solved, right? So after finding the value of x3, now we will try to find x2. So we will take this 2' equation and we are going to substitute the value of x3. So this is the 2' equation. So we have found the value of x3 here. Now we want to find the value of x2. So for this, we are going to, if I just write it in this way, a 2 prime x2, and it would be equals to b2 prime minus a 3 prime x3. From here we can easily calculate the value of x2. x2 would be equals to this b2 prime minus a 3 prime x3 divided by a 2 prime, right? So it would be the value of x2, and if you look carefully here, we have to substitute the value of x3, right? We have found the value of x3 in the previous step. Now we have to substitute its value here. That's why we are calling this step as backward substitution. We are finding the value of the unknowns in a backward manner and we are substituting its values. So it would be the value of x2 and now if you want to find the value of x1, we are going to take this one equation number 1, and so we are going to, if I just write one more line, we can write a11 x1 would be equals to b1 minus a12 x2 minus a13 x3. So from here we can find the value of x1 by just dividing this portion with a11. Okay, so this is the value of x1. So we can find all the values. So this step is the backward elimination step. Oh, backward substitution step, sorry, not elimination. Okay, so we can find all the value of the variables. So why did we learn about Gaussian elimination? Let's move back to the origin. The first thing was what? The first thing was the matrix inversion is not that much easy to perform whenever the system becomes larger. Gaussian elimination actually is a very, if I want to say, very time-saving technique whenever we want to implement it in code in MATLAB. Okay, so in MATLAB it becomes pretty much easier because what we are actually doing, we are just multiplying it with some coefficients and just doing some sort of subtraction. Not much. Not we are not taking, or we are not doing some rough calculation or difficult calculation. We are just multiplying with some coefficients and taking subtractions. So that's why we're actually picking Gaussian elimination. When the system becomes larger, Gaussian elimination performs better and faster than the matrix inversion. And we have seen how we can do Gaussian elimination. Okay, so this is the backward substitution step. Now we will move on to the code part. Before moving on to the code, so we will provide you the code for the Gaussian elimination, and you have to make some changes in the code that you will find in the lab sheet. Okay, let's discuss about it first, and then I will give you a break. It will be a prayer break for 10 minutes, and then we will move on to the code for details. So the thing that I said, that the general code for Gaussian elimination will be provided on Bucks. You will find the code for Gaussian elimination on Bucks. I will release the portions, but you have to make some modifications in those codes. Like in the labs, you have implemented the code for linear regression and the code for non-linear regression or polynomial regression was given. So in similar manner, the Gaussian elimination code will be provided, but you have to make some modification there. So what type of modification you need to do? So the first thing is you have to check whether a system is singular or not. Okay, so the approach that we have seen here is called actually naive Gaussian elimination. This technique is called the naive Gaussian elimination. This is called the naive Gaussian elimination. Naive means this approach is not that much smart. Okay, this approach is not that much smart. We can make this approach better. Okay, so after doing some modification, we will get the complete Gaussian elimination. And you have to modify the code yourself for the lab task. Okay, some modifications is required. Okay, so what type of modification is required? First thing is we will check whether the system is singular or not. Okay, so what I'm trying to say is that we call this matrix the coefficient matrix, right? We call this matrix the coefficient matrix. And if the coefficient matrix is a singular matrix, the system becomes unsolvable. Okay, for complete Gaussian method, we follow two approaches. One is the singularity check, of coefficient matrix, and the second step is pivoting. Now I will discuss about these two steps, okay, for making the code smarter, for making the code better. By the way, we have more other type of Gaussian elimination. We have Gauss-Jordan elimination as well. We only learned about naive Gaussian elimination till now, and now we will learn about complete Gaussian elimination. And in Math 216, I guess you are familiar with Gauss-Jordan elimination as well. We have one other type of elimination that's called the Gauss-Jordan elimination. We are not going to discuss about this in this course. It's called the Gauss-Jordan elimination. We are not going to discuss about this for now. Okay. So You will learn about it in Math 166. Okay, so now we will discuss about the first thing, that's singularity check of coefficient matrix, and then the pivoting. So why do we need to implement these two steps? Because complete Gaussian is more efficient, if I want to say, or smarter, if I want to say, than naive Gaussian elimination. I guess we can have a feel hearing the word naive. Naive means who is amateur, right? Naive means amateur, or who is not that much efficient, not someone like a pro. So you have to make this naive Gaussian elimination to a better code. For singularity check, we have the coefficient matrix. So we have the coefficient matrix. This is our coefficient matrix. So whenever the coefficient matrix, if we determine the determinant of these coefficient matrix and it becomes 0, we call the system singular. And singular system is unsolvable. Okay, let me repeat once again what I'm trying to say. If we have 3 unknowns, we need 3 equations, right? If we have 3 unknowns, we need 3 equations, right, to find the value of the unknowns. Can anyone make this statement or express this statement in a better way? Is 3 equations always sufficient to find the value of the 3 unknowns? Okay, let me repeat once again. If we have 3 equations, can we always confirm that we will find the value of the 3 unknowns? মানে আমাদের কাছে যদি তিনটা yes please
তিনটা লাগে স্যার।
আচ্ছা, তিনটা আননোন, তিনটা ইকুয়েশন থাকলে সব সময় কি আমরা খুঁজে বের করতে পারবো আননোন গুলোর ভ্যালু?
No, sir.
Yes,
নো স্যার। বলেন
স্যার।
yes
যতটা আননোন ততটা ইকুয়েশন লাগে স্যার।
যদি ইনকনসিস্টেন্ট হয় ইকুয়েশন গুলো তাহলে
exactly, here is the catch. The thing I tried, the statement that I uttered is that we need 3 equations to find the 3 unknowns. This statement is not complete. This statement has some loophole. This statement is not complete. We actually need 3 linearly independent equations. To find 3 unknowns. Okay, so if we have some sort of equation, if I just give you 3 unknown and 3 random equations, there is a possibility that you may not be able to find the solution from there. And in those cases, we call the systems inconsistent, that one of you mentioned. Like if I give you 3 equations that look like this, 5x plus thrice y minus twice z equals 9, and 2 more equations is that looks like this: x minus twice y, x minus twice y plus 9z equals 10, and I just multiplied the equation by 2. So twice x minus 4y plus 18 equals 20. So I have given you 3 equations and I am asking you to find the value of x, y, and z. Then in this case, you will not be able to find the value of x, y, and z, because these 2 equations are dependent on each other. these two equations are not linearly independent. Okay, so here is the catch, that if you have been given any equation, there is a possibility that you may not be able to find the solution. If I give you three equations that are linearly independent, then you will certainly be able to find the solution. If they're linearly independent, then you will certainly be able to find the solution. But if the equations are linearly dependent, then there is a loophole, right? So that's the thing we can check using this singularity check. So whenever you calculate the determinant of the coefficient matrix, whenever you calculate the determinant of the coefficient matrix and you get the determinant 0, then we call the system, or we call the matrix, a singular matrix, and it is unsolvable. Okay, so this type of situation arises. If this type of situation arises, you will see that the determinant will be 0. If you just take 5, 3, -2, 1, -2, 9, 2, -4, 18, and calculate the determinant of A, you will get 0. By the way, for calculating determinant of any matrix in MATLAB, we have a function called det. This is a predefined function. So just take the coefficient matrix and pass it through this det function and check whether the value is 0 or not. So if it is 0, then just stop there. We will not be able to find the solution, whatever we do. Okay, whatever we do, if the determinant of the coefficient matrix becomes 0, we will not be able to find the solution. Never ever we are going to find the solution. Okay, so first, so that's why we are calling these methods smarter. We are calling the complete Gaussian elimination a smarter approach, because if I see that the determinant of the coefficient matrix is 0, then I will stop there instantly. I will not try to solve anything. Okay, যদি আমি দেখি যে কোএফিশিয়েন্ট ম্যাট্রিক্সের নির্ণায়ক ডিটারমিনেন্টটা 0 হয়ে যাচ্ছে, তার মানে ওই সিস্টেম আনসলভেবল। ওইটা নিয়ে ধাক্কাধাক্কি করে আর কোনো লাভ নেই। আমি ওইটা নিয়ে যত মারামারি করি কোনো লাভ নেই। ঠিক আছে, কাজেই বেটার যে আমি ওখানে থেমে যাই। ঠিক আছে, দ্যাটস তাই জন্য এটাকে আমরা স্মার্টার অ্যাপ্রোচ বলছি। ওকে, সো the first thing is that after getting the coefficient matrix, we will check whether the determinant is 0 or not. If the determinant is 0, then stop there. If it's not, then we will further move on to our naive Gaussian elimination step. Okay, so that's the first step to get smarter, make our code efficient. Now we will move on to the second step, that's called the pivoting. Okay, so this is the singularity check. Now we will discuss about the pivoting step. Okay, so the pivoting step actually deals with a different case. If you can recall, in our Gaussian elimination, we divided the equations by the pivot elements, right? In our forward elimination step, we divided the pivot equations by the pivot elements, by A11. Right? We divided by A11. We divided here as well by A11, and in this case, we divided it by A22 prime. The pivot element was this. So, if in some case the pivot element becomes 0, what will happen? Let's assume we have a system of equation that looks like this. We have twice y minus thrice z equals 9. We have minus 5x plus 5x plus thrice y minus 9z equals to 6. We have let's make it plus 11x plus 4y minus z equals to minus 2. So, and I am giving you one more information that let's assume this equation is solvable. Okay, so this three equation is linearly independent. So as they're linearly independent, these three equations, so the system is solvable. But if we try to solve the equation using Gaussian elimination, what type of error or what type of difficulty we're going to face? Can anyone guess? Can you see that we are going to jump into a very difficult scenario here? We are going to jump into a very difficult error. We are going to face the math error that we see in our calculator. The coefficient for this term is 0, right? So if we try to solve this equation using Gaussian elimination, this is our pivot equation, right? And what we did, we take the pivot equation and divide it by this term. This is 0x actually. There is nothing present here. So this is 0x. The coefficient with x is 0, if I want to say. This is actually 0. Nothing present here means 0 is present. So we are going to divide the first equation by 0 and multiply it by minus 5, this term. Right? So dividing something by 0 is a mess. If we try to divide something by 0, we will get math error in our calculator. And here our code will just stop there. Okay, our code will just stop there. So what could be a probable solution? Can anyone guess? How can we avoid this situation? Our main target is to make the pivot element non-zero, and we call it pivoting.
Sir, can we swap the equations? As in, like,
Exactly. Exactly. Thank you so much. So that's the thing we are going to do, and we call it pivoting. So the idea, so it would be a mess. So pivoting means making the pivot elements non-zero, making sure that the pivot element is non-zero. Are non-zero. Okay, so what we can do, that one of your classmates suggests that we may swap the equations, right? So we have this thing with us, and what we can do, we can just swap the third equation with the first one. We are going to swap the third equation here and take the first equation down there. So in that case, our first equation will look something like this. This is the first equation. It would be our second equation. And our third equation will look something like this. And if you now look, we have the zero element as well here readily. So we don't have to do any sort of elimination process here. It is already eliminated. Right? So that's the thing. This thing is called pivoting. So whenever we have any pivot element as 0, we are going to swap the rows. We are actually swapping the rows. Swapping the equation means we are actually swapping the rows, right? So you have to implement this idea in your code, in the naive Gaussian elimination code that's provided. Okay, so you have to implement this idea in the lab sheet. You will get the pseudocode. Pseudocode means you will get the algorithm how you can do the pivoting step. You will get the algorithm and you will get the pseudocode as well. Pseudocode means uh, the language will look something like code, but you have to convert it in MATLAB. You will see. You will get some hint in the lab sheet how we can do the pivoting, but you have to do it yourself for the lab report submission. Okay, so that's called pivoting, and we actually refer it as partial pivoting whenever we swap the rows. Okay, so swapping rows is called rows, or rows means equations. We have swap the first and third equation. We call it partial pivoting, and partial pivoting is good enough. It is just fine for us. You have to do the partial pivoting in the lab report. One other solution you can think of. Can anyone guess what could be one other way to solve this problem? Instead of swapping rows, what we can swap?
So we can add the rows instead.
We can add. Okay, we can keep our thing simple. We may swap the columns as well if you wish. Add the coefficients for all the equations. Okay, we may do that, but we may swap the columns as well if you wish. Let's assume we are swapping the third column. We are taking this in the front. We are taking the z variable in the first place. Then we are taking the y variable. And then we can take the x variable in the last place. Right? So we can swap the columns as well if we wish. This is also valid. Okay, if we swap the columns, this is also valid. So we are actually swapping this column with this, right? And the constant will remain as it is. 6 minus 2. Okay. So the unknowns are as it is. Just we are considering the z unknown in the first place. That's the thing we are doing. Okay, and this is called I want to say this is called complete pivoting. You don't have to implement this thing. Swapping columns is called the complete pivoting. Columns, or column means we're actually swapping the variables, right? In the previous case we are swapping the equations, but now we are swapping the variables x, y, z. We are swapping x and z with each other. We call it a complete pivoting. You don't have to do complete pivoting for the lab report. Partial pivoting is good enough. We would be happy with this. Okay, so that's the idea of pivoting, and the idea for checking whether the coefficient matrix is singular or not, whether the system is consistent or not. Okay, so you have to modify the code for of the naive Gaussian elimination with these two idea to make the code better, more efficient and smarter. Okay, okay, now we will move on to the naive Gaussian elimination code. Would it be better if we take a small break, or should I continue? I guess most of the people have already left. Should we take a break, or You are okay if I continue?
Maybe we should take a break. পাস করা হয়েছে তো মাথায় না উঠতে পারে।
আচ্ছা, একটা ব্রেক নিলে ভালো হয়, তাই তো নাকি?
জি স্যার।
আচ্ছা, তাহলে আমরা একটা 10 মিনিটের ব্রেক নিচ্ছি। হ্যাঁ, এই ফাঁকে আপনারা একটু হাত মুখ ধুয়ে আসতে পারেন, খাওয়া দাওয়া করে আসতে পারেন, চাইলে আসরের নামাজও পড়ে ফেলতে পারেন। So it is 5:27. We are taking a break of 10 minutes. Hopefully, I will be back in 5:38. Okay, so you can have some snack. Uh, you can refresh yourself, and you can perform a prayer as well in this time. I'm coming back by 10 minutes. Thank you. Thank you so much for
থ্যাংক ইউ স্যার।
okay. Okay, I guess I'm back. Okay, so we will now continue to the code. I will try to explain the code and then we will end our session. So thank you for keeping up with me so long. And I'm going to share my screen with you. I will try to explain the naive Gaussian elimination code and then, okay, let me stop share the screen. Let's open MATLAB once again. Where is the code? Okay, so let me share my screen. Okay, so this is the code for the naive Gaussian elimination. I guess my screen is visible, right? Is my MATLAB screen visible to you?
Yes, sir.
Okay, thank you, thank you. So let's assume we have a system where the coefficients that looks like this. So this is the coefficient that some of your friends suggested, right? So we get this type of coefficients when we apply when we apply nodal analysis, right? When we implement nodal analysis, we get this type of coefficients, 1 over something v by r, this type of coefficients we get when we apply nodal analysis. So these are the coefficients for the coefficient matrix: first coefficient, then the second coefficient, the third coefficient. We have the other rows. So this is the coefficient matrix A and this is our constant matrix B, and we want to find the value of the voltages or the unknowns. So we are writing a function called naive Gaussian elimination. So this function takes input the coefficient matrix and takes input the constant matrix, the A and B that we have, right? The things that we worked with, these A matrix and this B matrix. Okay. So we are actually implementing a function, naive Gaussian elimination function, and we are giving input of these two, and we are getting two outputs from this function. The first one is the B. B is the augmented upper triangular matrix. Augmented upper triangular matrix means we will get these triangular matrix and the constant will be augmented with this. Okay, we will see how B looks like. You don't have to worry. So we are actually returning the upper triangular matrix and also the solution, the X, the value of the unknowns. Okay, so you can use this code whenever you will do math 216. As if you have done math 216, you can verify your row echelon forms by this code as well. Okay, if you run this code will perform the Gaussian elimination that we call row echelon form, right? You will find the row echelon form from this code as well, the Gaussian elimination format. Okay, so what is written inside this function, naive Gaussian elimination? So this is the function, the naive Gaussian elimination function, and you have to make some modifications here. Okay, you have to make the small modifications here to implement the singularity check and the pivoting that I discussed. You have to make the changes for the singularity check and the pivoting inside this function. These two functions will be provided. These two .m files will be provided on bus. Okay, you have to make the changes in this function, this naive Gaussian elimination. You have to first check whether, let's assume I'm giving you just some hint. What you can do, you can just put an if else condition, like if date of this A is equal 0, then you can just return. Return means we will go out of this code. Okay, we will return from this function without executing these lines. Okay, by the way, I should put an end here. So if the determinant becomes 0, just return from this function without performing these lines, without doing the Gaussian elimination and so on. Okay, so you can do this type of thing for singularity check, or you can write your code as well. Just think about it, how you can consider the modifications for singularity check.
Sir, could we not like if the determinant is 0, obviously we can't really do it. So can we never mind.
Okay, so you can do the other thing as well, like you can put a if block here that will check if determinant of A is not equal 0, then you will execute the code. Do you want to say this type of thing?
Yes, sir. I was gonna say this if when this was possible or not.
Exactly. So if the determinant is not equal 0, then just make the code giving a then after putting this if, then you can here give an end. Then inside this if block, it would run, this code would run. You can do this if you wish as well. If determinant is not equal 0, then we will run the code. Okay, just put the if condition here. You can do it as well if you wish. No worries. The way you want to solve, that's upon you. You have the independence how you can solve. So this is the part for the singularity check, and for the pivoting part, I will give you also an hint where you can include the steps. But first, try to explain what is written here. So first of all, we are doing or we are augmenting two matrices. Augmenting means we are actually joining two matrices. Joining means we considered as we tried to perform Gaussian elimination, we have to make the changes in the constant part as well, right? We have to make the changes in the constant parts as well. That's why we are making a matrix that looks like this. We are trying to augment these two matrices. Augment means we are actually joining the two matrices. Let me copy this thing. We have the A matrix, the coefficient matrix as this. We have the B matrix as this. And we are augmenting them and making the augmented matrix look like this. Augmenting means simply joining the elements. Oh, what's happening? Let me copy once again. We are actually increasing one column. So this is the augmented matrix. Okay. This is the augmented matrix. We call this matrix augmented matrix. So in this augmented matrix, actually the first row is representing the first equation, right? In this augmented matrix, if I want to say This first row is actually representing the first equation. This is the first equation. Then this is the second equation. And this is the third equation, right? The purpose of augmenting is that we want to make the changes in the constant part as well. That's why we are considering the coefficients of A and the constant B all together. All together we are doing the calculation. That's why we are augmenting it in the A matrix. Okay. So we are augmenting it in this way. After writing the A matrix, we are writing the B matrix by putting a space in between them. Then they gets augmented. Let me give you an example. Let's assume we have a matrix here called X that looks like this: 1, 2, 3, semicolon 4, 5, 6, semicolon 7, 8, 9. By the way, you can put comma if you wish. You can skip comma if you wish as well. To separate two elements, you can give a comma or you can just give a space. Both of them are same. Okay, so this is our X matrix, and let's assume our Y matrix looks like this: 100, 200, and 300. So this is our Y matrix, and if I just write something like this in third bracket, I'm writing X space Y, then these two matrices will be augmented. Okay, this Y would be just added as a separate column. Okay, so this is the thing we are doing here, and then we are calling the size function. The size function actually is having the row and columns. So if I just, okay, let me save it in some matrix M. So this is our M matrix, and we can see the M matrix has 3 rows and it has 4 columns, right? 1, 2, 3, 4 columns. So if I call the size function, size is a default function of MATLAB. On this M matrix, it will return us the number of rows and the number of columns. Okay, so if I hit enter, then the first thing is the number of rows. So we have 3 rows and we have 4 columns. Okay, so we can assign the values in R and C if I wish. R and C would be size of M. Then in the R variable, we will get the number of rows, 3. And in the C variable, we will get the number of columns, 4. Okay, so if I hit enter, then we can see R is 3 rows, and 4 columns. That's what we are expecting. Okay, so this size function actually helps us to determine the number of rows and columns of any matrix. Okay, so here we are assigning the number of rows in M variable. M is actually calculating how many rows are there, and N is calculating how many columns are there. Then this one single line actually performs a whole forward elimination step. Forward elimination step means the thing we did in this portion, like multiplying with some coefficient, dividing by the pivot element. The thing that we did here has been done by this single line of code. Okay, so what this line actually do? Let me explain. This is a very efficient line. So we have this augmented matrix with us. That's the first thing. So let me write it here. Copy করলে ঝামেলা করতেছে কেন? We have the augmented matrix with us. Okay, let me open a. So we have this augmented matrix with us, and now we will see what this code snippet is. And as I mentioned, the first row is actually representing the first equation, right? So this first row is actually the first equation. This is the first equation. This is the second equation. And this is the third equation, right? So if you can recall, we did not change the first equation in case of naive Gaussian elimination, right? We kept the first equation as it is. If you can recall, in the final format, okay, my OneNote is lagging a bit. In the final format, the first equation was kept as it is. We did not make any change in the first equation. We eliminated the terms starting from the second equation, right? We eliminated the terms starting from the second equation. That's why we are iterating a loop. So here is a loop written down here with the I coefficient. Okay, by the way, for our problem here, we have 3 rows, right? We have 3 rows, 1, 2, and 3. We have 3 rows and we have 4 columns, 1, 2, 3, and 4. So for our case, the value of m that was denoting the number of rows is 3, and the value of n that was denoting the number of columns is 4. So if you look at the first for loop, the first for loop is being executed for I equals 1 up to m minus 1. So m minus 1 actually represents what? We have the value 3 here. So 3 minus 1 is giving us 2. So the first for loop for this I, it is being executed for I equals 1 and 2. Starting from 1, let me make these things a bit larger. So starting from 1, if you can recall the operation colon actually means incrementing by 1, right? We are actually starting from 1. We will iterate or we will continue our loop up to m minus 1. M minus 1 means 2, right? So the first loop will be executed for I equals 1 and 2. Okay. Now moving on to the second loop. So this I loop will actually control the pivot equations. If I want to say, it will control the pivot equations. We actually dealt with 2 pivot equations, the first and the second. If you can recall, in our forward elimination step, we considered the first equation as the pivot equation, and then we considered the second equation as the pivot equation, right? So for I equals 1 and 2, we are actually controlling these 2 pivot equations. Okay, with this I parameter by the outer loop, we are actually controlling these 2 pivot equations. So when I will have value 1, we will see we will work with the first pivot equation, and when the I will become 2, we will see we will work with the second pivot equation. We will see, just wait for a bit. And with the J loop, the inner loop, the nested loop here, we can see the J loop is being iterated from I plus 1. So for whenever I is 1, the J loop will start from 2 up to m. Up to m means the value of m is 3, so it will iterate up to 3. Okay, let's start our iteration considering I equals 1 first. Okay, so let's first think we are considering the outer loop and we are considering I equals 1. So for this loop, the value of the j will be what? J will iterate I plus 1 up to m, right? I plus 1 means 1 plus 1, the value of I is 1. So 2 to m, value of m is 3. So j will iterate for 2 and 3. So let's first consider j equals 2. Then we will iterate for j equals 3. So inside this line, we are writing this thing. So what this thing is doing actually? This line is actually doing the 2 steps. Doing the 2 steps means multiplying by the coefficient that we want to eliminate and divide by the pivot element and doing the subtraction. We will see this whole thing is being done by that single line. We will see. So if I put the value of j and I here, what I will get, a j comma colon. J comma colon means okay, first write the thing, putting the value of j is 2. So 2 comma colon is equals a j comma colon once again. So a 2 comma colon, then we are writing a minus sign here. Then we are writing a I comma colon. Value of I is 1 now. So 1 comma colon. And we are dividing it by a I. So I'm giving a multiplying sign. We are dividing it by a 1, value of I is 1, and multiplying it by j a j I. The value of j is 2 comma 1. And with this thing, I am considering this augmented matrix side by side. Okay, so if you can recall, if we want to access any matrix, a 2 comma colon means the second row, if you can recall. If I just want to show you, we have this M matrix with us. Let's assume if you want to access only one single element, like this 2, if you want to get this value only, then you have to write in this manner, M, then you have to pass the row number. So this element is sitting in the first row. So 1, first row, and then give a comma. Then the column number. So this 2 is sitting in the second column, right? So first row, second column. So I want to access the value that's in the first row and in the second column. So if I hit enter, then I will get 2. Let's assume I want to access this 300 value. So what should I pass here? What's the row number here for this 300? This is a third row, right?
Yes.
So this is a third row. Oh, thank you. Okay, so this is a third row, and if I want to mention the column, this is in the fourth column, right? So 3 comma 4. Oh, 3 comma 4, right? We have to write it 3 comma 4 because we want to access this 300 value. It is on the fourth column. So if I hit enter, we get 300. So this is the way how we can access one single element. So what would be the case if I want to access this whole row, because this is our first equation now. Our target is to access this whole row because this is the first equation. This is a pivot equation now. So for accessing all the elements, let's assume this is our M matrix. Let's assume I want to access this second row, the whole second row. So then what I have to write, M second row. So I have to put 2, then put a comma here. Then which columns do I want to access? I want to access all the 4 columns, right? I want to access all the 4 columns. So I can write it in 2 different ways. The easiest way is to put a colon. A colon means I want to access the second row and all the columns here. See, if I hit enter, then we are getting the second row. So can anyone say how to access this third column?
We just do the opposite technically. We go M and then we put a colon, and since we want the third column, which is
yes, so colon, comma, 3. So it means all the rows and the third column. So third column, all the rows. 3 is in the first row, 6 in the second row, 9 in the third row. So if I hit enter, then we get 369. So this is the significance of the colon operator. Okay. So now move back to our code. So what we are actually doing here, if I focus on this, a 1 comma colon means I am actually considering the first equation, the first row. This first row is actually representing the first equation. So this is our equation number 1. This part is equation number 1. Now if I look at this, a 2 comma 1, it means second row, first column, this element, right? A 2 comma 1. So we are multiplying the first equation with a 2 1, and if I look at this coefficient, a 1 1, first row, first column, so this element, right? So we are dividing it by a 1 1. That was the thing we were doing in the first step, multiplying the pivot element with the coefficient we want to eliminate and divide it by the pivot element, right? And then we are subtracting this whole portion. This whole portion is being subtracted. We have a minus sign here, is being subtracted from the second row. This thing actually denotes the second row, 2 comma colon, right? So this is the second equation actually. So we are subtracting this whole part from the second equation, and we are putting it in the second row. After modifying this, we are putting it in the second row. That's the thing we have done here, and that's how we eliminated the first term. We eliminate this term in this way, multiplying with a 2 1 divided by a 1 1 and then subtracting it from the second equation. We have eliminated this term. Okay, so for j equals 2, this thing is happening. So whenever, so after that, the value of j will get increased. J will iterate up to 3, right? Here is the condition for j. J will iterate for 2 and up to 3. So the value of j will get increased. So j will become 3. So if I write this line once again, considering the value of j, so we have a j comma colon. So value of j is 3 now. So a 3 comma colon. This is equals to a j comma colon, means a 3 comma colon minus a I comma colon. The value of I is still 1. Value of I is still 1. By the way, we have eliminated this term already. A 2-1 term has been eliminated. This term has been eliminated. Now we want to eliminate this term, a 3-1 term. That's why we are doing this thing. So the value of I is still 1 because the pivot equation is still the first equation. So a I comma colon, this part, I comma colon means 1 comma colon, and we are multiplying this by this coefficient and dividing it by this coefficient. So dividing it by a I means what? A 1 comma 1, value of I is 1. Should be lower, and multiplying it by a j comma I. Value of j is 3 now. So 3, I is 1, 3 comma 1. So the same thing we're doing here. This is the first equation. This is the equation number 1. This coefficient a 3 comma 1. A 3 comma 1 will give us access to these element, a 3 1 element. So we are multiplying it by a 3 1, and we are dividing it by a 1 1, the pivot element, this element, dividing it by a 1 1. So this is the modified pivot equation, and then we are subtracting it from the third equation. Right? This is the third equation. So after performing this operation, and we are updating it in the third row, we are updating all the coefficients in the third row. So after doing this thing, we would be able to eliminate these coefficient as well. These coefficients would be eliminated. Okay. Then if you look carefully, then the value of I would be increased. This nested loop would finish to run. This nested loop would be executed, and then we will move back to the outer loop here for the ith loop. I will then get increased to the value of 2. I will reach to value of 2. And in that case, if you look carefully, j would run for what? The value of j is I plus 1 up to m. As I is now 2, I is now 2 here. So I plus 1 means 2 plus 1. It means 3 up to m. The value of m is 3 also. So 3 to 3. So j will iterate for once, and the value of j would be 3. So the value of j would be 3. So I guess you are having a feeling what would happen now. If I just copy this thing, we are going to eliminate these elements now. It's A32. And for eliminating A32, our pivot equation was the second one. If you can recall, for eliminating these terms, our pivot equation was the second equation, and our pivot element was this. So now this thing will happen. Okay, so if you just iterate the loop by putting the value of I and j, you will see. Okay, let me just copy this thing. Let's try to iterate it as well. So if I try to execute this line, a j comma colon, it means what? A 3 comma colon is equals a j comma colon. So a 3 comma colon minus a I comma colon. Value of I is 2 now because we want to focus on the second equation right now. So a 2 comma colon it is being multiplied by j comma I. So a j comma I, value of j is 3 now. So 3 comma 2 and divided by this portion a I, the pivot element. I is 2 now. So a 2 2. So if I copy the augmented matrix as well, so what we are doing here now, a 2 comma colon, 2 comma colon means this is the second equation now. This is our pivot equation, right? This is pivot equation, and we are multiplying it with a 3 2 third row second column, third row second column. It means this element, right? Third row second column. So we are multiplying it by a 3 2 and we are dividing it by a 2 2. It means second row second column, second row second column, this element. We are dividing it by a 2 2, and after getting this we are subtracting it from the third equation. This is the third equation, right? So after performing this, we are updating the coefficients in the third equation, so the third row. So after performing this, what will happen? These coefficient will be eliminated. A 3 2 coefficient will be eliminated. Okay, so that's the thing we did actually in case of forward elimination, right? In the forward elimination step, we did the same thing actually. With the second equation, we multiplied with these two coefficients, and then we took the subtraction. Then our forward elimination is done. Okay. So the I loop would finish as well. The I was supposed to iterate from 1 to 2. So we considered I equals 1, we considered I equals 2. So this loop would finish and our forward elimination step would also be completed. Okay. So this is the first portion of the naive Gaussian elimination. By the way, so if you want to incorporate pivoting in your code, then what you have to do, you have to incorporate the code before this line, right? Because we don't want to divide by 0 in case of our elimination. So you can incorporate your code here, if I want to say. Your pivoting code might be incorporated here. You should think about it where you should incorporate your code, but one way could be to write or include your pivoting code here. Okay, so try to modify the code for pivoting here. Okay, you can incorporate this code here. Then after pivoting, we can move on to the elimination part. Okay, so that's the thing here, and then comes the last step, the backward substitution, right? So if I just snip this part once again, I'm going to explain it fast. After this portion, our session will be ended. So just keep up with me for some more minutes. So this is the backward substitution portion. For the backward substitution part, first what we are doing, we are introducing the X matrix or the X vector initialized with zeros. By the way, for our case, the value of M was 3, the number of rows, and the value of N was 4, the number of columns. So the X vector would contain the value of x1, x2, and x3. Okay, so we are initializing the X vector with 3 zeros, and then we will update the values. We will calculate x1 here, then we will calculate x2 here, and calculate x3 here. Okay, for initializing any vector or matrix as zeros in MATLAB, we use this function, this zeros function. This is a default function in MATLAB. Let me show you. Let's assume you want a matrix that is having 5 rows and 3 columns. Then you should write something like this. Zeros, sorry. You want 5 rows and 3 columns of a matrix, and all the elements should be 0. Whenever we initialize any variable, we generally initialize it with 0, right? Whenever we write code in C or any programming language and we need to initialize any variable, it is a very common practice that we initialize the variable by 0. That's why we use this zeros function. So this zeros function will help us to initialize a matrix by having rows, 5 rows and 3 columns. Okay, so if I hit enter, then you will see a matrix has been initialized. So you can give any name of this matrix. So let's assume I'm giving the name of the matrix as M2 or whatever. So if I hit enter, so our M2 matrix would be this: 5 rows and 3 columns. All the elements are 0. So what we are writing here, we are writing here x is equals zeros 1 comma n minus 1. So we are writing actually zeros 1 comma n minus 1. The value of n is 4. N minus 1 is giving us 3, right? N minus 1 is 3. So zeros 1 comma 3. It means we want a matrix having 1 row and 3 columns. So we are actually doing this thing: 1 row and 3 columns, and for each of the column we will update the value of x1, x2, x3. We will do this thing the rest of the part of the code. We'll calculate the value of x1, x2, and x3. Okay, we are initialized the variable vector, and then we will update the values. Okay, so now if you can recall, in the backward substitution step, the first step was to calculate the last unknown, right? The x3 was calculated. We were able to calculate x3 first. In the backward substitution step, we were able to calculate x3 first. Okay, let me copy this thing as well. So our augmented matrix is having this format. As we have eliminated this term, let me copy this thing. We have eliminated these terms, right? We have eliminated in the forward elimination step, and now our augmented matrix is our augmented matrix looks like this. If I want to write, our augmented matrix looks like this: A11, then A12, then let me write it in this way: A11, then A12, then A13, and here we have the B1, then we have 0, then A22 prime, A23 prime, B2 prime, then we have a 0 here as well. We have a 0 here, and we have A33 prime and B3 double prime. So our augmented matrix is having this format. I'm writing it here because it will be easier for me to explain the code now. So this is the augmented matrix now we have. A matrix. We'll delete this portion for now. After performing the forward elimination, we have this thing with us. So now we will calculate x3 first, right? We can calculate x3 first. So that's why we're writing this line, the second line. Excuse me. So what does this line do? The value of m is 3 for us, the number of rows, right? The value of m is 3. So we're calculating xm. It means x3. I'm focusing on this line. X3 is equals amn. If I write it as the value of m is 3, m is 3 and n is 4, right? A 3 comma 4, and we're dividing it by a m comma n minus 1. N minus 1 will give us 3 as well. So what's in here? If I look carefully, a 3 comma 4, what do we get in this position of our augmented matrix? A 3 comma 4 means third row, fourth columns. Third row, fourth columns. So we get B3 double prime. So this is actually B3 double prime. And what do we get from here? A 3 3 means third row, third column. So these elements, A 3 3 prime. So if you can recall, the value of x3 was this exactly. If I just move back, well, it should be a 3 3 double prime. So where was x3? X3 was this thing exactly. B, if I just copy this thing, x3 was exactly this thing. By the way, it should be a 3 3 double prime. Okay, so the value of x3 has been calculated by this line. We have calculated the last variable x3, and we are placing it in the third position of the x vector. X3 means this is the first position, the index is 1 here, this is the second position, and this is the third position. So we are putting the value of x3 here. We have calculated the value of x3 and we are updating the 0 value. So this is now B3 double prime divided by a 3 3 double prime. We are updating this position. We have calculated the x3 variable. Okay, now we will move on to the calculation of x2 and x1. I will move fast. So for this portion, we need to execute these two loops, and it is pretty much easy. I will explain one and you will understand the other one just if you try. So we have a nested loop here as well. For this, the I is being executed from m minus 1. So the value of I, m minus 1, we have m equals 3. M minus 1 gives us 2. Then we are decrementing by 1. We are having a decrement operation. So we will decrement and reach up to 1, 2 and 1. So the outer loop will run for I equals 2, and then the outer loop will run for I equals 1. Okay. So okay, let me snip this part once again. I will take not more than 5 or 7 minutes. Okay, just give me 7 or 8 minutes. I'm not going to take more than that. Just place it here. So as the value of m is 3, this loop will run for I equals m minus 1. It will start iterating from 2, and we will decrement by 1 and reach to the value 1. So the first of all, the value of I would be 2, and when the value of I is 2, we will calculate the value of x2, and when the value of I becomes 1, we will calculate x1. Okay, we have already calculated x3. We have already calculated x3. When the value of I is 2, we will calculate x2, and then when I becomes 1, we will calculate x1. And then we are initializing a variable called sum to 0. We are keeping it. So the sum variable is having 0 now. And then in the inside loop with the j parameter, j would be iterate for I plus 1 up to m. So we are considering I 2. So I plus 1 will give us 3, and m is also 3. So this is 3, and this is 3 as well, right? So the I plus 1, so the value of j would be I plus 1, I is 2, so I plus 1 will give us 3, and it will iterate up to m. The value of m is 3 as well. So j will iterate for once for j equals 3. So inside this loop, we are updating the value of the sum variable. So we are updating the sum variable. So we are updating the sum variable with the previous sum value. Previously sum was 0, right? Previously sum was 0. So sum is equals 0 plus aij. Aij means what? The value of I is 2. So a2 comma j is 3. A2j, and it is multiplied by xj. The value of j is 3, x3. So I'm copying the A matrix here. This is our A matrix, and this is our X matrix. Right? So this is our, actually, if I want to say, this is the X1. This is the X2, and this is the X3. So now, if I want to calculate the sum variable, what we are doing here, we are multiplying A23 with X3. So A23 is what? The second row, third column, right? So the second row, third column, this thing. So this sum is actually having this, the sum variable. 0 is 0. We are multiplying A23 prime with x3, right? X3 is this. X3 is this, right? So I can write it simply as x3 because it will be easier to understand. This is the x3 value, the third parameter. So for j equals 3, the inside loop is done. Then we break from this loop. And for the outer loop, we are calculating the xi. So if I write this line, xi, for the outer loop, xi, the value of I is 2. So x2 is equals ai comma n minus sum. So I is 2, 2 comma n is 4, m was 3, and n was 4. So I comma n gives us a 2,4 minus the value of the sum. So this is the sum portion we have. And we are dividing it by AII. Value of I is 2. So we're dividing it by a 2, right? So we are dividing this whole thing by a 2. So if I put the values here, what do we have in a 2,4? If I focus on a 2,4, second row, fourth column. So second row, fourth column, we are getting this thing, B2 prime. So I can write, we are calculating B2 prime, this thing, second row, fourth column, minus a 2,3 prime x3 divided by a 2,2. What do we have at a 2,2? Second row, second column. Second row, second column, this thing, a 2,2 prime. And we are assigning it in x2. We are assigning the value in x2. It means we are updating the x2 variable, this portion. We are updating the x2. So we have this thing here now. And if I just move back and see at the x2 variables value, we actually did the same thing. If I just copy and paste it here, then you can see we are actually doing the same thing here. Okay. And you will see, so this variable has also been calculated, and then the I will get decreased by 1, then I will become 1. I was supposed to iterate from 2 and then it will become 1. So the I would become 1 once again. And just do this iteration yourself and you will see the x1 would be calculated. X1 would be calculated and you can match the value if you wish. You'll see the same thing we will get whenever the I becomes 1. Okay. So that's the code. That's the code for the naive Gaussian elimination. Just run the code for now. So let's assume we have these coefficient matrix with us, A, and we have this constant matrix with us. Okay, let me put semicolons instead of. Okay, so if I run the code, then you will see the augmented matrix has been returned. It means from here you can get the row echelon form as well. Row echelon form means in Math 216, I guess you had to do this type of things. You had to find the matrix after performing the Gaussian elimination. So you will get the matrix as well here after performing the Gaussian elimination. This element has become 0, this element has become 0, and it has become 0. So you will find the row echelon form matrix and you will get the solutions as well. So these are the 3 solutions. This is the x1, this is the x2, and this is the x3. Okay, so these 3 are the 3 solutions, and this is the modified augmented matrix, the row echelon form. Okay, so that's it about the code for for the Gaussian elimination, naive Gaussian elimination. What you have to do, you have to run some code for the Gaussian elimination and you have to modify the code to make it better. You have to implement the idea of complete Gaussian elimination for the lab report. Okay. Okay, that's it. I guess that's it for now. I guess we can end the session for today. So thank you. Thanks.
স্যার এই কোডগুলো কি স্যার নেক্সট মানে সিমুলেশন এক্সামের জন্য থাকবে স্যার?
হ্যাঁ, কোডগুলো বাক্সে অ্যাভেলেবল থাকবে, আপনারা ওখান থেকে চাইলে অ্যাক্সেস করে নিতে পারবেন। ঠিক আছে, কোডগুলো
স্যার এগুলো কি সিলেবাসে থাকবে এক্সামের জন্য?
হ্যাঁ, এই থার্ড এক্সপেরিমেন্ট পর্যন্ত থাকবে। ঠিক আছে, এমনি যে কোড আপনাদের অনেক বুঝতে হবে তা না, বা কোড যে অনেক কিছু করতে হবে তা না, মূলত এই কোডগুলো ইমপ্লিমেন্ট করে ইমপ্লিমেন্ট করতে পারতে হবে, মানে একটা সিস্টেম দেওয়া থাকবে, সিস্টেম থেকে সলিউশনটা খুঁজে বার করে আনতে হবে। হ্যাঁ, এই কোড দেখে খুব বেশি ঘাবড়ানোর কিছু নাই, মানে এগুলো নিয়ে খুব বেশি ঘাবড়ানোর কিছু না। আপনাদের এখানে খুব বেশি কিছু করতে হবে না, ল্যাব শিটে হয়তো করতে হবে। হ্যাঁ, এক্সাম নেক্সট
এক্সামের টাইমে কি স্যার নিউ মানে কোড করতে হবে না স্যার কোশ্চেন থেকে?
কোশ্চেন থেকে কোড করতে হবে, একদম অনেক কিছু করে করতে হবে তা না, আপনাদের মোটামুটি কিছু মডিফাই করতে হবে। সো ইন দ্য এক্সাম ইউ ডোন্ট হ্যাভ টু রাইট, you need not have to write the code from the scratch, but you have to make some modifications for the code to implement or find the solutions. Okay,
ওকে স্যার।
you don't have to write the codes from the scratch. We will solve some problems in the next session, then it will be easier for you to understand. No worries. Okay. Okay.
স্যার
Thank
একটা আমার প্রিভিয়াস স্যার একটা অনলাইন ক্লাসে প্রেজেন্ট ছিলাম, কিন্তু স্যার অ্যাটেন্ডেন্সটা মানে মিস করে গেছিলাম।
আচ্ছা,
এটা কি একটু দেওয়া যাবে?
আচ্ছা, এই চ্যাট বক্সে তাহলে লিখে দেন, চ্যাট বক্সে লিখে দেন ডেট সহ কোন ক্লাস মিস করেছিলেন সেটা, চ্যাট বক্স সেটা লিখে দেন একটু চ্যাট বক্সে।
স্যার ডেটটা তো মনে নেই স্যার এক্স্যাক্টলি।
আচ্ছা, রিগ্রেশন ইন্টারপোলেশন, আচ্ছা ঠিক আছে, আপনি তাহলে একটু ডেটটা সহ তো লিখতে হবে, নাহলে তো আমি কেমনে বলবো, বা কোন সেশনে ছিলেন সেটা বলতে পারেন?
মানে স্যার লাস্ট অনলাইন ক্লাসের আগের ক্লাসটা।
এখান থেকে ট্রেস ব্যাক করতে পারবেন স্যাটারডে ধরে ধরে 5 তারিখ?
5 তারিখে তো আমাদের ইয়া হয়েছিল, মানে ফিজিক্যালি ক্লাস হয়েছিল। তার আগের ক্লাসের মানে 19 ফেব্রুয়ারি স্যার।
আচ্ছা 19, তাহলে একটু আপনার আইডিটা লেখেন আর পাশে 19 ফেব্রুয়ারি লেখেন, তাইলে আমি ট্রেস ব্যাক করতে পারবো। চ্যাট বক্সে লিখে দেন আইডি আর পাশে 19 ফেব্রুয়ারি লিখে দেন। Okay, thank you so much for keeping up with me for so long. Hope to see you in the next Friday. Thank you so much. Happy holiday for the next Saturday. Thank you.
স্যার দিয়ে দিয়েছি।
ঠিক আছে, থ্যাংক ইউ।
ওকে স্যার।